Sleep and study. Don't forget to subscribe.
As we consider a broader variety of potentials when we solve the time-independent Schrödinger equation, we get a broader variety of solutions. The potentials that we're considering next have a couple of unique conceptual features that I'd like to talk about in a little more detail. Essentially, the difference between a bound state and a scattering state is the difference between the solutions to the free particle potential and the solutions for the, say, harmonic oscillator potential. We'll also talk a little bit about quantum tunneling, which is an interesting feature that can be used in a lot of ways in terms of practical applications, for instance, in quantum tunneling microscopy. But what we're going to talk about in this lecture is just a conceptual overview of these features. First off, let's consider what happens classically. If we have a potential, v of x, if you imagine having a little cart, for instance, rolling around on some sloped surface, this would then be the gravitational potential. And you know a cart in this position is going to be accelerating downwards, downhill, and it's going to roll around and roll back up until it reaches the height at which it started, until it reaches the same potential at which it started. To put this in a framework that makes a little more sense quantum mechanically, if I have some energy level, total energy level, for our cart, if it starts here with zero initial velocity, that level of its energy is essentially the total energy. Its potential energy at that point is its total energy. As the cart rolls downhill, it gains kinetic energy, having its maximum kinetic energy at the lowest point here. Then it rolls back up until it runs out of kinetic energy at the far point here. So we have effectively an allowed region here. The cart will never be found at higher potentials here or higher potentials here. So our allowed region covers the region between these 2 points, which are called turning points, since that's where the cart turns around. The space between the turning points depends, of course, on the energy level. If I had a cart, for instance, with an energy level here, either it could roll around on this side of the hump here, or it could roll around on this side of the hump. If it's on this side, you'll just have oscillations back and forth here. If it's on this side, you'll have oscillations back and forth here. If I continue to even lower energies, down here, my allowed region becomes smaller still, until I have just 2 turning points here, and the cart would just slowly wiggle back and forth between these 2 turning points. Classically speaking, it's not possible to have a particle with energy down here. This is not allowed. Essentially, the cart doesn't have enough energy at all to be on this surface. You'd have to lift the cart off the floor and place it in your bowl, for instance. This is for one particular type of potential, in particular one that goes up to infinity for large negative and large positive values of x. We can have other sorts of obstacle for our cart to roll over, for instance like a bump in the rug. If our cart comes in with enough kinetic energy to roll over this hill, we might say it has some energy up here, in which case the allowed region is, well, everywhere, all the way out to negative and positive infinity. If our cart doesn't have quite enough energy to clear the hump, then our allowed region is either just to the left of the hump or just to the right of the hump. A cart that does not have enough kinetic energy to clear this hill will roll up the hill, stop, and then turn back. A cart rolling in from the other direction would roll up the hill, stop, and turn back. So that's what we would expect a classical object like a cart rolling around on a surface, for instance, to make an analogy between this potential energy v of x and the gravitational potential energy. That's what the behavior of such a cart would look like. Quantum mechanically, we have a different picture. You know what happened in the quantum harmonic oscillator when we talked about a particular energy level. Consider an energy level here. The general behavior of the wave function psi depended on whether we had a potential energy that was higher than the energy that we were working with, or lower than the energy that we were working with. So for instance, if I say the energy of the separation constant E in the derivation of the time-independent Schrödinger equation, the energy of the stationary state, if the energy is greater than the potential at a given point, then our psi curves towards the axis. We get sort of wave-like behavior for psi if the energy is greater than the potential. Now, if you remember what happened if the energy was less than the potential, we got wave functions that curved away from the axis. And that generally posed a problem for our normalization unless we were sort of pointed towards the axis the right amount, such that curvature away from the axis led to the wave function just coming and kissing the axis and then never leaving again. This is just from consideration of the behavior of the time-independent Schrödinger equation at a particular energy. If you think about, for instance, a constant potential. Energy above the potential leads to curving towards the axis, sort of wave-like behavior, whereas energy less than the potential leads to curvature away from the axis. Either wave functions that go on to join the axis or wave functions that curve away from the axis and cause problems for normalization. So in the case of this arbitrary potential now, what our wave function might look like, I'll plot psi in green here. In regions where the potential is larger than the energy, we know we have to have this sort of coming towards the axis to kiss the axis sort of behavior, something like that. We have to have that on both sides. Otherwise, we'll have a wave function that's not normalizable. In between, we have to have some sort of wave behavior. Since the energy now is above the potential, and we're going to have curvature towards the axis. Now, I haven't tried to make this a rigorous sort of solution, but this is what your wave function might look like. What that means is that the allowed region, the region where we'll find the particle, is the region where we have some wave function that is, non-zero. And we have wave function that's non-zero, even beyond the classical turning points. So our classical allowed region would be in between these two turning points. But our quantum allowed region is going to continue out past. And it's not going to have particularly sharp boundaries here. This would be our quantum allowed region, going all the way out, even beyond the classical turning points. So this is a little bit different. Another scenario in which we have this region extending beyond what would be considered allowed classically is if we have an energy level, say, in this region. If our energy of our stationary state falls in this region, our quantum allowed region is again going to extend beyond the classical turning points here. It's going to even span across this small region here. So in spite of the fact that our overall energy is lower than the potential here, we still have some probability of finding the particle there. This is different than our classical behavior. One comforting fact is that the energy, a quantum particle having a stationary state energy below the potential everywhere is still not allowed. And you can understand what might happen with that, because everywhere having an energy below the potential means that everywhere you have the wave function curving away from the axis. So if the wave function is, say, coming down to kiss the axis here, because we know we need something normalizable, it's just going to keep curving away from the axis here, and we'll get something that is completely non-normalizable. Same thing happens if I try to make it kiss the axis on this side. I'll get something that blows up in the positive direction. So we're still not allowed to have energies below, but for limited regions. Here the energy of the wave function is below the potential, but this is a finite region. So we can have this sort of coming down to kiss the axis behavior. Same thing sort of holds for this region, except we don't have to have the wave function come down to completely reach the axis here. We could have a solution that looked something like this, for instance. If our wave function is, curving towards the axis here, then coming down, instead of to kiss the axis, just curving away from the axis, but then now the potential being smaller than the energy level again means we're curving towards the axis. And I need to draw this slightly better, curving towards the axis until here, when again the potential is higher, and then we have to come down to kiss the axis because we're running out of space. You can have the same sort of thing happen on this side, curving towards the axis since our potential is smaller than our energy, and then over here coming down and over to kiss the axis. So our wave function never really came to kiss the axis in this central region. We never quite ran out of amplitude of our wave function, if you want to think about it that way, in our curving away from the wave function, but we didn't have any problems with normalization either. These regions where the potential is larger than the energy can still have, in principle, some probability of finding the particle there. For the case of our hill potential, we can still have quantum mechanical states that have energies higher than the peak energy in the hill. And for those states, our quantum allowed region is going to be all space. For quantum mechanical states with energy below the highest peak of the hill, we can again have this sort of behavior where we have a quantum, I forgot to turn off my ruler, quantum allowed region on either side, and spanning all the way through. We have a quantum allowed region everywhere. And we'll find out what wave functions look like that satisfy this sort of potential later on. We know we're going to have wave-like behavior here, wave-like behavior here. In the middle here, we're going to have wave function curving away from the axis. So just to try and draw something, we might have something that looks like this. Let me try again here. Wave function that looks like this. Now in this region where the potential is higher than the energy, we curve away from the axis, and then start curving back towards the axis again on the other side. So our wave function might look like this, but it's going to extend to both positive and negative infinity. This sort of, the solution to the time-independent Schrödinger equation at regions away from our hill looks like our free particle solution. Since we have a constant potential, we might as well set that constant potential equal to 0. So essentially what we've got here is free particles on one side, free particles on the other side, connected by some region where it doesn't look as much like a free particle, but it still has some probability of finding the particle there. If you had, for instance, a traveling wave coming in from the left here, you would have a traveling wave going out to the right on the other side. So your particle, which has not enough energy to clear the hill, still somehow makes it through. This is called tunneling. And the probability of a particle passing through a barrier that's essentially impossible for a classically equivalent particle to cross is the phenomena of quantum tunneling. If you imagine what would happen classically, your cart coming in here is going to roll up the hill, stop, and turn back. It will never, ever magically pass over the hill. The absurd analogy that people like to use for this is imagine walking through a door without bothering to open it. There's some energy necessary to pass through the door, and in the case of something like a human being passing through a door, that energy would be very, very large. But it is in theory possible for you to pass through the door without interacting with it. It just has a very, very small probability of happening. If this barrier were extraordinarily large, you would have enough curvature away from the axis that it would be very difficult to normalize your wave function unless it came down and kissed the axis. And that's what we're working with in classical physics. But just briefly to summarize those two terms, or those two sorts of states, for potentials that looked like something like this, like the harmonic oscillator potential, we have energy levels that result in states that cannot exist in certain regions. So we have confined states, confined wave functions. This is what we mean by saying something is a bound state, that the wave function is confined. Since the wave function is confined, it's normalizable, and the exact number of waves, for instance, that fit in the region that would be classically allowed in the quantum mechanical case is usually quantized by the boundary conditions. Scattering states, on the other hand, if we have a potential that looks, say something like this, where we have energy levels that are above the lowest, those wave functions will extend to infinity because there's no reason that you can't find the particle here. As a consequence, they're non-normalizable, And since we don't have any boundary conditions that are requiring something very specific about the value of the wave function as it comes down to kiss the axis in this case, or in the case of a free particle, we don't have that. We can have the wave function do whatever the heck it wants as it goes out to infinity. We don't have a quantized spectrum. We don't have any boundary conditions to induce quantization. So you end up with a continuous distribution of energies. There's nothing to prevent energies of basically any value in this region. It's even possible to have potentials that have both. For instance, if I had an energy level down here, I could have wave-like behavior here, and then coming down to kiss the axis on either side. This sort of looks like a quantum harmonic oscillator state. This sort of looks like a free particle state. So it's possible to have both for the same potential. The other process that I mentioned, quantum tunneling, happens for potentials that look like a barrier, where the particle classically would not be able to pass through the barrier because it doesn't have enough energy. But quantum mechanically, the allowed region includes even the barrier and extends on both sides of the barrier. So that's bound states, scattering states, and tunneling. To check your understanding, consider the potential shown in orange here, V of x, and describe the states that exist at particular energy levels, whether they're free or bound, for instance, where you would be likely to find the particle if you were to observe it at a particular energy level, for example. Second question, does this potential have bound state solutions? And third question, does this potential have scattering solutions? Not bound scattering solutions. Ignore that word. Scattering state solutions. When you're trying to solve the time-independent Schrödinger equation for a complicated potential, for instance, a potential V of x that's defined as a function of one region and then another region having a separate function, you may end up with a well-defined solution in region 1 and a well-defined solution in region 2. For instance, if we had, say, a psi of x that was wave-like in region 1 and behaved differently in region 2, for instance, just smoothly curving down to join with the axis, it's useful to be able to combine these two solutions. And the question then is, how do they match up at the boundary? This is the question of boundary conditions, which is the subject of this lecture. The boundary conditions that you need to match two solutions of the Schrödinger equation, the time-independent Schrödinger equation now, can be determined more or less from consideration of the time-independent Schrödinger equation. What is the allowed behavior of a solution? We've discussed the time-independent Schrödinger equation in detail. You know now that this is the kinetic energy operator, and this is in some sense the potential energy operator. But let's focus on the kinetic energy operator, since it has this second derivative of psi. That's where we're going to get a good notion for what's allowed of psi and what's not allowed of psi. Suppose we had a step discontinuity. Is that allowed? What our psi would look like under those circumstances is something like this. Maybe we have a psi that comes in on one side and goes out on the other. If this happens in an infinitely narrow region, we say psi is step discontinuous here. If we wanted to look at, for instance, the kinetic energy associated with a step discontinuity like this, we're going to need to take a second derivative of psi. So if I take the first derivative of psi, the first derivative of a step function is a delta function. If it's not obvious why that's the case, think about what you would get if you integrated from one side of the delta function to the other side of the delta function. If you integrate from, say, a point here to a point here, you'll get 0. If you integrate from a point here to a point here, you'll get 1. Or you'll get some multiple of 1, depending on if you're, say, multiplying by a delta function, like 3 times a delta function or 5 times a delta function. You get 3 or you get 5. So as a function of integrating from this point to this point, you would get 0, 0, 0, 0, 0, some constant, and then increasing your upper limit on your integration doesn't change your final answer. So integrating a delta function from some point on one side of the delta to some variable point gets you a step. And that's more or less, if you go back to the fundamental theorem of calculus, what you expect if you say integrate the derivative as a function of the upper limit of the integral. So the first derivative of our wave function psi here gives us a delta function. If I take then a further derivative, the second derivative with respect to x of my wave function psi, what I'm going to get is going to be the derivative of a delta function. It's going to be 0 away from the step and go both to positive and negative infinity at the location of the step. So the derivative of a delta function is a little bit strange. This is going to, first derivative is going to act like a delta function, second derivative is going to act like a derivative of a delta function. What does that mean? Well, consider calculating the expected value of the kinetic energy. The expected value of the kinetic energy can be expressed as an integral of the complex conjugate of the wave function times kinetic energy operator acting on the wave function itself, integral dx. Now, if we're looking at a discontinuity here, the second derivative of our wave function, which is what we get if we're looking at the kinetic energy operator, is the derivative of a delta function. So we're going to end up with something that's the integral of psi star times the derivative of a delta function. I'm leaving off proportionality constants because I'm more or less just trying to argue whether or not this is feasible. So don't quote these as strict mathematical equalities. Looking at this, you know what taking the integral of a function multiplied by the derivative of a delta function is. If not, think about this as integration by parts. You can push the derivative off of the delta on to the psi star, and you just get then an integral of psi star times a delta function. This is discussed in the lecture on the behavior of the delta function. So what this is going to give us is the integral of the derivative of psi with respect to x, psi star, times delta of x dx. Now this is an integral we can do. It's just going to pull out the value of the derivative of psi star. But what's the derivative of psi star? Well, the derivative of psi acted like a delta function. So essentially we're going to have delta of x times delta of x, integral dx. And this is a problem. You can think about integrating this first delta function as multiplied by some arbitrary function as pulling out the value of the arbitrary function at the location selected by the first delta function. So this is effectively going to give us delta of 0, which you know is infinity. This is a problem. The expected value of the kinetic energy being infinity means that whenever I observe this particle, I could get an infinite kinetic energy. That's a problem. So this is essentially not allowed. What that means is that psi is continuous. The other interesting condition that I'd like to discuss is what happens if we have a discontinuity not in psi, but in d psi dx. What this means is that my wave function would look like this. Coming in at one angle, and then having a kink at the boundary. So instead of having a discontinuity in psi itself, we now have a discontinuity in the first derivative of psi. The slope of psi changes discontinuously. If you look at the Schrödinger equation for this, this is kind of problematic. We're taking the second derivative of psi. The first derivative of psi is now going to have a step discontinuity, so the derivative of the first derivative is going to look like this. It's going to look like a delta function. What that means is, to draw that out, d squared psi dx squared plotted as a function of position is going to look like a delta function the second derivative of psi goes to zero, or goes to infinity at the discontinuity. But this isn't necessarily a problem, because there are other pieces of this equation that we could balance things out with. For instance, if the potential goes to infinity at the boundary, we might have something that we can work with. So this is a problem unless v of x goes to infinity. So this is the sort of allowed behavior that we can have from the wave function. It's always going to be continuous because any discontinuity in the wave function itself gives us effectively infinite kinetic energy. And the first derivative of psi is also going to be continuous unless we have an infinite potential. What this means from the perspective of boundary conditions, what we're talking about now is we have two regions, region 1 and region 2, and they're separated by some boundary. Let's say this boundary happens at some position x0. We have solutions on one side of x0 and we have solutions on the other side of x0. And the solutions within region 1 are fine. Psi sub 1 is continuous, and the first derivative of psi sub 1 is also continuous. Same thing holds for region 2. Psi 2 is continuous, and the first derivative of psi 2 is continuous. At our boundary, we have something special happen, and we change over from solutions in region 1 to solutions in region 2. What that means is that at the boundary, we have to have allowed behavior for psi, and what that means is that psi 1 evaluated at x0 must be equal to psi 2 evaluated at x0. This says psi is continuous at the boundary. This is necessary in order to prevent our overall wave function from having effectively infinite kinetic energy. That's our first boundary condition when we're matching two solutions together. The second boundary condition, the second consideration we had in terms of allowed behavior of psi, concerned the first derivative. So unless we have v of x go to infinity at x0, we have d psi 1, and I'll write this slightly differently, d psi 1 dx evaluated at x0 must be equal to d psi 2 dx evaluated at x0. What this says is d psi dx is continuous at our boundary. This is our second major boundary condition, and this holds unless v of x goes to infinity at the boundary. The potential that we're going to consider next is actually a delta function, which means we will have the potential going to infinity at the boundary. And we'll have to consider in more detail what happens when you take the derivative of a wave function, or what happens to the first derivative of the wave function at the point where the potential goes to infinity. But overall, these are our boundary conditions for the wave function, solely on the basis of consideration of allowed behavior of psi. As an example, consider a potential step. What this looks like as a function of position is we have a potential on one side that discontinuously changes to the potential to some new value of the potential. Considering what happens, and we will consider this in a lot of detail later on, is suppose we have an energy of our particle here. This would be, say, the energy. On this side, we know we have wave-like solutions. This is sort of our free particle case. So if we're going to have wave-like solutions here for our wave function psi, on the other side of this boundary, we know we have to have psi curving away from the axis since the potential is higher than the energy. And if we're going to have something normalizable, we have to have the wave function just sort of come in and kiss the axis. So we're going to have solutions in this region, and the solutions in this region are, we'll see, actually end up looking like e to the minus x. And we have solutions in this region that look like sine of x. And if we're going to match solutions that look like sine of x to solutions that look like e to the minus x, we're going to have to carefully tune the constants that multiply each of these. And we're going to have to actually consider also adding a phase to this sine function. So we have 2 degrees of freedom here, our normalization and the relative position of this function on the axis. And we have our degrees of freedom in this region as well. And in order to come up with something that satisfactorily solves the Schrödinger equation, we'll have to match our constants. We'll have to have the right value of the energy, we'll have to have the right normalization of our sine function, we'll have to have the right relative position of our sine function, and we'll have to have the right relative amplitude of our exponential function. And we'll discuss this in excruciating detail when we get to talking about the finite potential well, where essentially we have 2 steps. And we're curious what sort of states we can have that are confined to the space. But for now, that sums up our boundary conditions. I'm going to go back a slide just to highlight them again. The wave function itself is continuous, and the first derivative of the wave function is continuous unless the potential goes to infinity. Over the past few lectures, we've developed the machinery necessary to solve the time-independent Schrödinger equation with a potential given by a delta function. We've talked about bound and scattering states, and the delta function potential will actually have both solutions, or both types of solution. And we've talked about boundary conditions, which will help us match solutions in the areas away from the delta function, where we can easily express the solutions, we'll be able to make those solutions match at the delta function itself. So, what we're working with is a delta function potential, v of x, and v of x under these circumstances looks something like this. It's 0 everywhere except at a specific point. So we're looking now at v of x as a function of x. It's 0 everywhere except at the origin here, x equals 0. And there it goes to negative infinity. I'm defining v of x to be minus a times delta of x because we don't necessarily know exactly what the strength of this delta function potential is. You can have different strengths of delta function. If you treat a delta function as a distribution, of course, it has to be normalized. But in this case, we're treating it as a representation of a potential. So we need some constant here which determines the strength of the potential relative to sort of a unit normalized potential. What our solutions will look like under these circumstances depend on the energy of the solution. For instance, if we have an energy up here, E greater than 0, we know we have, in these regions away from x equals 0, we know we have sort of traveling wave solutions. We don't know exactly what happens at x equals 0 here, but we know these are going to look like solutions to our free particle potential, which we discussed a few lectures ago. On the other hand, if we have an energy below 0, then we know what the solutions have to look like. When our energy is below our potential, our solutions have to curve away from the axis. And if we're going to have something normalizable, we need to have the solutions eventually, as they curve away from the axis, instead of curving up to infinity or curving down to minus infinity, they have to just sort of smoothly join in with the axis itself. And we have to have that on both sides of the boundary. But we still don't know what exactly happens at the boundary. That's where our boundary condition matching comes in. But first of all, let's consider what the solution looks like away from the boundary. And in this lecture, I'm going to focus on the bound state, the state where the energy of the state is less than 0. For the bound states, energy less than 0, if what we're looking at is away from x equals 0, then we know v of x is equal to 0. So our time-independent Schrödinger equation becomes minus h bar squared over 2m times the second derivative of psi with respect to x. is going to be equal to E times psi. We know the energy now is negative, so we're going to have a negative quantity on the left and a negative quantity on the right. In order to consolidate some constants, let's consider moving the 2m over h bar squared over to the right-hand side here by multiplying through 2m over h bar squared. We'll end up then with d squared dx squared of psi is equal to k squared psi, where I'm defining k to be equal to something that looks a little strange, square root of minus 2me all over h bar. To make the signs clear here, energy is negative, so what we're actually looking at here is the square root of a positive number. We've got a negative energy, positive mass, and negative from the minus sign, negative from the energy. So we're taking the square root of a negative quantity here, so our k constant here is going to be real. Looking at our equation here, you can look at this and think second derivative is giving me something squared times my wave function back. Well, I know what the solution to that sort of differential equation is. It's psi of x is equal to a e to the minus kx plus b e to the kx. This is our general solution, and as is typical in quantum mechanics, if what we're going to have is normalizable, then we can set some conditions on this. Our actual space looks like this. We have, as a function of x, our potential is blowing up at x equals 0. So we know we have a solution away from x equals 0. That's what we're trying to find here. If we want a solution on the right here for x greater than 0, and we want our wave function to be normalizable, we know we have to have b equals to 0, because if we have a non-zero b, integrating, say, the squared modulus of the wave function from 0 to infinity will give us infinity, because we have something growing exponentially here. So for x greater than 0, we know b must be equal to 0. Similarly, for x less than 0, we have to have a equal to 0, because otherwise we have something growing exponentially as x goes to minus infinity. What our overall solution then will look like is in region 1 here, let's say psi 1 of x is going to be equal to a times e to the minus k, or to the e to the kx, whereas in region 2 we're going to have our solution psi 2 is equal to b e to the kx with the minus sign. So e to the minus kx over here, e to the kx over here. What our solution then is going to look like overall is something like this and something like this, and we still don't know exactly what happens at the boundary. So let's figure out what actually happens at the boundary. Our boundary conditions, and we had two of them, was first of all that psi was continuous, and second of all that the first derivative of psi was continuous unless the potential went to infinity. Let's consider the first of those boundary conditions here. Psi continuous. In order to have psi continuous, what this means is that in our regions here we have psi 1 on the left and psi 2 on the right of x equals 0 here. If we're going to match these two conditions continuously, we have to have psi 1 of x equals 0 equal to psi 2 of x equals 0. If I evaluate my solution on the left at the boundary and my solution on the right at the boundary, I have to get continuity, I have to get equality. So if we go back to our general solution, we had our psi 1 was, flipping back a slide a moment to get my a's and b's straight, our psi 1 was a times an exponential growing with x, and psi 2 was b times an exponential decaying with x. So going forwards a slide, our solution in region 1 is a e to the kx. If I'm evaluating that at x equals 0, I have to get something that's equal to b times e to the minus kx evaluated at x equals 0. Now when I evaluate the exponential parts here at x equals 0, I'm substituting in 0 in the exponent. Anything to the 0 is 0, or is 1. So both of these terms become 1, and I'm just left with a equals b. That helps a lot. but it doesn't tell us everything. Our second boundary condition was that the first derivative of the wave function, d psi dx, was continuous. But it's actually not continuous in this case. We had a condition on this boundary condition. We can only apply this boundary condition when the potential remains finite. And in this case, we have a delta function potential at the origin, so we're going to actually break this boundary condition in this case. We're not going to break it beyond all hope of recovery, though. The question is, what does d psi dx do at the boundary? The way to solve this problem is to go back to the Schrödinger equation, the time-independent Schrödinger equation, and keep in mind that our potential now is delta of x. It's a delta function. We actually had a minus sign and an a in front of that. So if we go back and think about what happens with delta functions. Delta functions are only really meaningful when you treat them as distributions and integrate. The trick here, then, is to think about integrating the Schrödinger equation. Where does it make sense to integrate the Schrödinger equation? Well, I don't know anything about the solution. Well, I know everything about the solution away from the boundary, but I don't know what happens at the boundary. So let's just integrate over the boundary. Let's integrate from, say, minus epsilon to epsilon, just integrating over the boundary. To rewrite that, what we've got is minus h bar squared over 2m times the integral from minus epsilon to epsilon of second derivative of psi with respect to x squared. That's our first term. Then substituting in for our delta function, we have minus a integral from minus epsilon to epsilon of delta of x psi of x. And then on the right-hand side, we have an integral from minus epsilon to epsilon of energy, which is a constant and can come out, psi of x. All of these integrals, and I've left them off all over the place, are taken with respect to x. So we have three separate integrals here, and we can figure out what each of these terms look like. Our left-hand term, we have the integral with respect to x of a second derivative. So that's easy. We're just going to get the first derivative. Minus h bar squared over 2m times d psi dx evaluated at the endpoints, epsilon and minus epsilon. So far so good. The second term here, we have minus a, and now we just have a delta function in an integral. Delta functions just pull out the value of whatever else is in the integral wherever the delta function, or wherever the argument of the delta function goes to 0. In this case, delta of x is going to pull out the x equals 0 value of psi. So this is just going to give me psi of 0. On the right-hand side here, I'm going to get something. But the key point about this integral is that we're only integrating over the boundary. We're going from minus epsilon to epsilon. You can probably see where I'm going with this. I'm going to let epsilon be a very small number. As minus epsilon goes to epsilon, or as epsilon goes to 0, I'm essentially integrating this function psi from 0 to 0. So I'm not going to get anything meaningful here. I'm just going to get 0. So this is actually all right. What we've gotten from consideration of integrating the time-independent Schrödinger equation over the boundary with the delta function potential is a condition that tells us how much our first derivative changes at the boundary. If I rearrange this expression here, I'm getting derivative of psi with respect to x evaluated at epsilon minus what I get if I evaluate it at minus epsilon. That's just equal to, rearranging my constants, what is it going to be equal to? Minus to 2ma over h bar squared times psi of 0. So that's actually pretty nice to work with. Let me try and move this over a little bit to give myself more space to work. And what we're left with then is substituting our general expression for our solutions for psi, now away from the boundary, into this expression. So we had d psi dx, evaluating this at positive values of epsilon means I'm in region 2, I'm on the right, which means I'm working with psi 2, evaluating that at x equals 0 on the boundary, subtracting d psi 1 dx, evaluated at x equals 0. So for now I'm letting epsilon go to 0, and I'm looking at just the values of the first derivatives. This is our left-hand side over here. We can substitute in values for that because we know what these expressions are, and furthermore, we know that a is equal to b in our expressions for the general solution. So if you refer back to our definitions earlier, what you get here, you're taking the derivative of an exponential, which brings down the k, and we get minus bk e to the minus kx, and we're evaluating this e to the minus kx at x equals 0. So this e to the minus kx is just going to go to 1. So I'm not going to bother writing it. I just get minus bk for the first derivative of psi in region 2 at the boundary. For the first derivative of psi in region 1 at the boundary, now I'm subtracting it because this is the second endpoint. I get a very similar expression. Again, bk e to the now plus kx. And again, evaluating this at 0 means my e to the kx is just going to be 1. The right-hand side now, we had constants minus 2ma over h bar squared, and then the value of psi at 0, is just going to be b e to the plus or minus kx. Again, substituting in x equals 0. It doesn't matter if I'm considering the plus or the minus, region 1 or region 2. This is still going to be just 1. So far so good. I can cancel out all of my b's. And what I'm left with, when I simplify a little bit, is minus 2k being equal to minus 2ma over h bar squared. This is the sort of condition we got when we were looking at how the boundary conditions affected the solution to the particle in a box potential, the infinite square well potential. When we actually looked at what the boundary conditions required, and in the case of the particle in a box, it was that the wave function went to 0 at the endpoints of the box, we got quantization. We have quantization again here, except we have a strict equality. There are really no more unknowns in this expression. If you manipulate this further, k equals ma over h bar squared, keeping in mind that k is equal to the square root of minus 2me, where e is a negative number, over h bar, you can solve for the energy. And what you get is that energy is equal to minus ma squared over 2 h bar squared. We have quantized energies. What our wave function then looks like, so far, what we know is that psi of x is equal to, on the left, e, and now substituting back in to the definition for k, e to the ma(x) over h bar squared, if x is less than 0, and e minus ma(x) over h bar squared, if x is greater than 0. Now, all of this had a b multiplying it out front, which I canceled out here. So my first derivative boundary condition did not help me find b. But there's one more fact that we know about wave functions like this, and that is that the wave function has to be normalized. So if you want to normalize this, you calculate the normalization integral, which you all should know by now. Integral of psi star psi dx has to be equal to 1. You can substitute in this definition for psi, set it equal to 1, do the integral, and find out what b is. This was one of our activities on day 4, so refer back to day 4 if you want to see a little bit about how to normalize a wave function like this. To summarize our results, this is what our normalized bound state solution actually looks like. What you find for the normalization constant is the square root of ma over h bar out front. And now instead of writing it as a piecewise function for positive and negative x, I'm expressing this as an absolute value of x in the exponent. The energy associated with this was minus ma squared over 2h bar squared. We are quantized, but we only have one bound state solution, singular, and this is what it looks like. For a delta function potential, you get these two exponentials decaying as x moves away from the origin. To check your understanding, consider the following two questions. Why is there only a single bound state? And can any initial condition be expressed as a superposition of bound state solutions in this case? We've developed the machinery to solve the time-independent Schrödinger equation for the delta function potential by connecting solutions covering the regions away from the delta function and matching them together with boundary conditions at the delta function itself. The last lecture discussed the bound state solution. This lecture discusses the scattering state solutions. To put this in context, what we're talking about is the potential v of x given in terms of a Dirac delta function. A now is just a constant that defines how strong the delta function actually is. So our potential is everywhere 0, except at some point where it goes to negative infinity. This is a plot now of v of x as a function of x. What we discussed in the last lecture was the bound state solution. What happens if we have an energy E of our state that's less than the potential, less than 0, less than the potential away from the delta function? And what we got was a wave function psi of x that looks something like this. Going down towards 0, away from the actual position of the delta function. I haven't done a very good job drawing this, but I think you get the idea. The scattering state solutions, by contrast, have energy greater than 0. So we're talking about solutions with energy E up here. At regions away from the delta function, we have basically the behavior of a free particle. We get traveling waves at regions away from the delta function, away from x equals 0. We don't really know what happens at the origin, but we know what our solutions should look like, and we should be able to use our boundary condition matching to figure out what happens at the origin. So what do our scattering states look like? Well, away from x equals 0, we have v of x is equal to 0. That means our Schrödinger equation, the time-independent Schrödinger equation, looks like minus h bar squared over 2m times the second derivative of psi with respect to x. No potential now is just equal to E times psi, where energy now is strictly greater than 0. We can manipulate our constants, much how we did when we were talking about the bound state, and express this as d squared psi dx squared equals minus k squared psi. Now I'm defining a slightly different k than when I was talking about the bound state solution because we have a different sign for the energy. Instead of having k be a negative or imaginary now, I'm going to again have k be positive and real by saying k is equal to the square root of 2me over h bar. If you recall, when I was talking about the bound state, I had e less than 0 and I had a minus sign inside this expression. Looking at this ordinary differential equation, we can write down the solution. And the solution is, let's say psi is equal to a e to the I kx plus b e to the minus I kx. When we take the second derivative of this exponential, we'll bring down an ik quantity squared, which will give us a minus k squared. Since we're talking only about regions away from the delta function, we really actually have two general solutions here. We have psi1 for regions for, say, x less than 0, and we have psi2 for x greater than 0. Psi2 now, to the right of the delta function, is going to look very similar, and it's going to be f e to the ikx plus g e to the minus ikx. I should write this as a capital G, sorry. Instead of saying c and d, I've jumped ahead to f and g to eliminate any possible ambiguity if we have to assign future constants, for example, e. So, we have our two general solutions covering regions for negative x and for positive x. What happens at the boundary? How do we match these solutions up? Our boundary condition matching, in terms of these two general solutions, is a two-stage process. We have two distinct boundary conditions, and the first is that psi is continuous. What that means is that psi1 of 0, our solution for negative x, evaluated at the boundary at x equals 0, must be equal to psi2 of 0, our solution for positive x's evaluated at the boundary. If I substitute 0 in for these exponentials, for x in these exponentials, what I end up with here is reasonably straightforward. A plus b equals f plus g. That's the result of our continuity boundary condition. And it helps, but it doesn't help all that much. We only get a single equation out of this, so we need to do more. The first derivative boundary condition is that the first derivative of psi is continuous, provided that the potential is finite. However, in this case, our potential is given by delta of x, which does not remain finite at x equals 0. The trick that we used when we were discussing the bound state solution was to effectively integrate the Schrödinger equation dx from one side of the boundary, minus epsilon, to the other side of the boundary, plus epsilon. When we integrate this, we should still have an equality, integrating the terms on the left-hand side and integrating the terms on the right-hand side. And knowing the properties of the delta function, we can simplify this integral greatly. I refer you back to the notes for the last lecture to see what this actually works out to be. What it tells you is that d psi dx, the first derivative of psi, which we get from integrating the second derivative of psi, evaluated at epsilon, and then subtracting the value evaluated at minus epsilon, essentially the change in the first derivative as we go from one side of the boundary to the other, is equal to minus 2 times m times a, the strength of our potential, over h bar squared, times psi evaluated at 0. The right-hand side here we actually got from the integral of our delta function times psi. So this is our boundary condition here, appropriate for use with delta function potentials. This tells us about the behavior of the first derivative of psi as we cross the boundary. So we're going to need to know what our first derivatives actually are. Well, psi1 was equal to a e to the I kx plus b e to the minus I kx. So if I take the first derivative of this and evaluate it at effectively 0, some very small quantity, what I'm going to get for d psi1 dx evaluated at 0, essentially, plus or minus epsilon. I'm looking at psi1 now, so I'm talking about the negative half plane, negative x's. What I get is ik is going to come down from both of these, and I'm going to get an a minus b. I can do the same sort of thing for psi2, which was equal to f e to the I kx plus g e to the minus I kx. When I take the first derivative of this, d psi2 dx, and evaluate it at the boundary, I'll end up with ik times f minus g, by similar reasoning. That means the left-hand side here, which I can calculate by looking at the derivative of psi for positive values of x as x goes to 0, this expression, and subtracting the first derivative of psi for negative values of x as x goes to 0, this expression, what I end up with is ik times f minus g minus ik times a minus b. That's the left-hand side now of our expression up here. Our right-hand side is minus 2ma over h bar squared times the value of psi at x equals 0. Now, if you look at either one of these definitions, you can see what happens when we substitute in x equals 0. We get a plus b for this one, or f plus g for this one, and I have a bit of a choice as to which one I want to use. In this case, I'm going to use a plus b, and you'll see why in a moment. What we end up with now, if you manipulate this expression a little bit and define a useful constant, in this case the constant is going to be beta, just to save some writing. Beta is defined to be ma over h bar squared k. What we end up with is f minus g is equal to a 1 plus 2I beta minus b 1 minus 2i beta. And this is the result of our first derivative boundary condition. There's effectively no restriction on these solutions so far. We have something similar to what we had for the free particle. There were no boundaries that were terribly restrictive. We did not end up with a quantization condition. We did not end up with enough of a restriction on our solutions that we ended up with something straight normalizable. But we have our two equations now involving a, b, f, and g. That, unfortunately, is two equations to go with four unknowns. We have our definitions of psi in terms of a, b, f, and g, and these e to the I kx, e to the I minus kx, e to the minus I kx. And then we have our two equations relating a and b and f and g. It seems like we're not going to be able to come up with a very rigorous solution here. But we can actually do a little better if we start thinking about what the initial conditions might actually be. First of all, note that these solutions are the spatial part, and if we add a temporal part to come up with an overall solution for an overall wave function, we'll end up with the same sort of traveling wave states that we had for the free particle. The time dependence for those states was essentially e to the minus I e t over h bar. If you look at each of these terms, you can see this is a plus I kx going with a minus I e t. As time increases, space must increase here in order to maintain a constant phase. So, as in our discussion of traveling waves, the plus I kx here for positive values of k is associated with the wave propagating to the right. So if you think about our boundary here at x equals 0, in the space to the left of the boundary, where we're considering psi 1, we have a wave coming in from the left, whose amplitude is given by a. Conversely, the term with b in it here is associated with e to the minus I kx. That represents a wave traveling away from our boundary with amplitude b. Likewise, in region 2, where we have f and g, we have a wave f traveling away from the boundary and a wave g traveling towards the boundary. Considering the initial conditions now, we have waves going towards and away from the boundary on both sides. If the initial conditions I am interested in are, for instance, our initial conditions are, say, scattering from the left, what we're interested in then is waves incident from the left. If you imagine waves coming in from the left, you may have some waves going out to the left by scattering waves off of your boundary. We may also have some transmitted waves propagating off to the right, but we will not have any waves incident from the right. What that means is that if we're interested in waves scattering from the left, we can say g is equal to 0. This is not a requirement. This is just a sort of useful restriction on our solution to allow us to interpret what we're looking at in a little more detail. The second key fact now is if we're looking at scattering from the left, A is effectively our incident wave. If you think about the physicist as an active part of this system, shooting waves in from the left, A is effectively an input. So we don't necessarily care about the value of A itself, it's something that we set. You could say set A equal to 1, if you wanted, in a suitable experiment. So G is 0, and A is our incident wave. As such, going back to these equations, we can cross G out, because G is equal to 0, and we can look for things in terms of A. We don't necessarily need to know A. We can find, for instance, F in terms of A, and B in terms of A, by appropriate manipulation of these equations. That will tell us what F is and what B is in terms of A, which is something that we set. So that's all right. Instead of having 4 unknowns, if we set G equal to 0, we have 3 unknowns. And if we say I as an experimenter am setting A, then I know A. So I really only have 2 unknowns, F and B. And if you go through that exercise and solve for F and B, what you end up with is B is equal to I beta over 1 minus I beta A, and f is equal to 1 over 1 minus I beta A. So this tells us what B is in terms of A and what f is in terms of A. That's pretty good. What I'm getting at now is if I send a wave in from the left, that's represented by amplitude A, I can calculate an amplitude B on the basis of amplitude A. Really what I'm interested in is the ratio of the amplitude squared of B and the amplitude squared of A, because that's telling me about the probability amplitude of the left-going scattered wave. Something incident from the left scatters back to the left, a reflection event. Whereas f, if I look at the squared amplitude of f, that's the probability magnitude of a wave propagating through the barrier. I send a wave in from the left, and it propagates through the barrier. This is a transmission event. So if I look at reflection and transmission in terms of my definitions, or in terms of my solutions for B in terms of A, or f in terms of A, you can think about the probability of reflection, R, being defined as the squared magnitude of B divided by the squared magnitude of A. If I send more A in, I should get more B out. These things have an exact ratio, and really this number is what's most important. And if you look at that, you can calculate that out pretty easily. It's beta squared over 1 plus beta squared. That's called our reflection coefficient. Our transmission coefficient T, being defined by the squared magnitude of f over the squared magnitude of A, again, looks very similar to B, except we have 1 over 1 plus beta squared for the transmission coefficient. So these are our definitions of reflection and transmission coefficient in terms of ratios of probability amplitudes. If I send an amplitude A in, I'll get what is the probability, what is the fraction of particles that are going to scatter back, essentially, as represented by a ratio. If I express these in terms of the definitions of beta and k, which, if you recall, beta was defined to be ma over h bar squared k, and k was defined to be square root of 2me over h bar, what we end up with for our reflection coefficient is 1 over 1 plus 2 h bar squared e over ma squared. And for our transmission coefficient, we get 1 over 1 plus ma squared over 2 h bar squared e. So, looking at these two expressions, you can easily see that if I add the reflection coefficient and the transmission coefficient together, r plus t, I get 1. This is good. And if you look at my reflection and transmission coefficients in terms of the energy, if the energy increases here, the denominator overall increases, and our reflection coefficient gets smaller. So for higher energy incident waves, the reflection coefficient decreases. That makes sense. The more energy you have when you're approaching a barrier, the more likely you are to penetrate the barrier. The transmission coefficient, by contrast, has the energy in the denominator now. So if energy increases, this quantity decreases, the overall denominator gets closer to 1, and the transmission coefficient gets closer to 1, as is required by the sum of reflection plus transmission probabilities is equal to 1. So that is more or less the gist. This is the key result of looking at scattering in the context of a delta function, in this case a delta function well. You can calculate quantities called the reflection and transmission coefficients purely from quantum mechanical considerations that tells you how much of the wave will reflect back and how much of the wave will be transmitted. For instance, if I had some wave packet, when I construct a wave packet, I'll have a spread in energies, but I can look at these reflection and transmission coefficients essentially averaged over the range of energies that I need to construct my wave packet as the effective probability that that wave packet will be reflected back or transmitted through. One final note now. If we have a delta function barrier, my reflection and transmission coefficients actually don't change. The delta function barrier instead of a delta function well means I'm going to be looking at something like this instead of something like this. Or these now are infinitely narrow delta function distributions. How I defined things originally here was that v of x was equal to minus a times delta of x. So essentially, my barrier now is just a negative value of a. A is less than 0. And if I swap the sign on a squared doesn't change. So my reflection and transmission coefficients remain unchanged. That's very interesting. What we would have had classically is that if a is greater than 0, we have a well, we would have had transmission coefficient equal to 1 and reflection coefficient equal to 0. This is your cart rolling on a track that has a dip in it. Your cart rolls down the well, picks up speed, rolls up the well, loses speed, and then leaves with exactly the same speed as it entered. It certainly would never be reflected back, certainly not only some probabilistic fraction of the time. If I have a less than 0, I have a barrier. In classical physics, that would mean I have transmission coefficient equal to 0 and reflection coefficient equal to 1. This is what happens when you have your cart rolling up towards a hill, except it doesn't have enough energy to go over the top of the hill. In this case, since we're talking about a delta function, the hill is infinitely high. It's also infinitely narrow, but that doesn't matter from the classical perspective. The cart will roll up the hill the amount it needs to in order to run out of kinetic energy, at which point it will stop, turn around, and roll back. You'll have no transmission and 100% reflection. Quantum mechanically, we get the same thing. Whether we have a well or a barrier, the reflection and transmission coefficients are unchanged. This is an example of what I mentioned earlier as quantum tunneling. Quantum tunneling, where the particle penetrates a barrier that it does not have enough energy to clear, is an especially easy thing to calculate in the context of a delta function like this. But really, this is kind of a remarkable result. One way in which quantum tunneling like this is used, and I have a very small space here to attempt to explain this, is in quantum tunneling microscopy. What that means is you have your substrate. In this case, say it's a bunch of silicon atoms on a wafer. Quantum tunneling microscopy involves taking an electrode, a very sharp electrode, itself, made of atoms, say it's only a single atom sharp, and looking at the rate at which particles are able to jump from the surface, the substrate, to your electrode. The electrode is not actually touching the surface, so we can look at this as having, say, as a function of height, let's look at, say, v of z now. You have a relatively low potential energy for electrons being in your electrode, a very high potential energy for electrons being in the free space between your electrode and the surface, and then again a low potential energy for the electrons being in the surface. And we'll look at this in the context of the next potential that we'll be considering, the finite square well potential. You can calculate the probability of a particle tunneling, jumping from the surface to your electrode, and it turns out the current of, if you're looking at electrons, jumping from the surface to your electrode is very sensitive to the distance that the electrode is from the surface, which allows you to make a very sensitive measurement of the height of the surface. And if you look up scanning tunneling microscopy, you can actually get images of the individual atoms on the surface, subatomic resolution, with a microscope, which is really pretty cool. To check your understanding, here are two questions to interpret what actually happens in the case of scattering states for the delta function potential. The last example to a solution to the time-independent Schrödinger equation that we're going to see in this chapter is the finite square well. We've seen the infinite square well. That was a potential that diverged to infinity for particle positions outside of certain region, 0 to a. The finite square well is analogous, except the potential does not diverge to infinity, it only goes to a finite value. The potential overall that we're going to look at is defined like this. There's some region from minus A to A where there is a well in the potential, some negative V0 value for the potential. At regions outside, greater than A or less than minus A, the potential is 0. We can expect solutions that look more or less like the sorts of things that we've seen. Suppose we had some energy level here. If this was the energy level and we wanted to know what the wave function might look like, we expect the lowest energy wave function to look something like this. In regions where the energy is above the potential, your wave function curves towards the axis, and in regions where your energy is below the potential, it curves away from the axis. In order to have things that are normalizable, we have to have our wave function come down and just barely join the axis. And you get states that look sort of like this. Curving shape joining with two other curving shapes that merge in smoothly with the axis. We know from our discussion of boundary conditions that at these boundaries here, the wave function itself will be continuous, there will be no jumps in the wave function, and there will be no jumps in the derivative of the wave function either. So that's what we expect to find. In the case of the infinite square well, there were an infinite number of states. We may find a similar behavior for this, but you wouldn't expect there to be an infinite number of states to remain bound within the well, since every time we raise the energy, the state becomes closer and closer to a scattering state that is not bound. Well, let's see what these bound state solutions actually look like. The general solutions that we're working with, we have three regions. We have a region to the left of the well, a region in the center of the well, and a region to the right of the well. So let's say this is minus A and this is A in some imaginary x-axis to this panel. For x less than minus A, if we're looking for a bound state, we know the energy is less than the potential. For minus A is less than x is less than A, we know the energy is greater than the potential. And for x greater than A, we know the energy is back to being less than the potential. So those are the sorts of solutions that we're working with. The time-independent Schrödinger equation, regardless of region, and I'll just write it on the bottom here since I'll probably have space, is minus h bar squared over 2m psi plus v of x psi equals e psi. So if you consider this as our Schrödinger equation, regions where the energy is less than the potential, we can rearrange this, and it's going to end up looking something like the second partial derivative with respect to x of psi is some positive number times psi, where the positive number here is essentially the energy being negative added to the potential energy being positive when we take care of the signs and rearrange our constants. What our equation will look like, if we're going to write it this way, the second partial derivative of psi is equal to some constant which I'll call k squared psi. We've seen solutions like this before to the for the bound states in the delta function potential, for example. K here is defined to be the square root of minus 2me over h bar squared. Let me move the h bar outside of the square root here and just leave it as h bar in the denominator. You've seen constants like this before, and this looks a little strange, like we're taking the square root of a negative number, but keep in mind here that e itself is a negative number. So we have a negative e, we're multiplying it by a negative 2, so we have a positive number inside the radical here. So k is a real positive number. The general solutions we get to equations like this, psi of x is equal to a e to the minus kx plus b e to the kx. This now being for x's which can be potentially large and negative. If we're going to have something normalizable, we need the wave function to go to 0 for large negative x's. That means we have to have a equals to 0 here. We have to be able to throw out this term, because if I plug in some large negative value for x, I'll get a large positive value for e to the minus kx. So the overall solutions we're looking at here in this region look like b e to the kx. We don't know anything about b, we don't yet know anything about k other than its definition in terms of the energy. In the central region, we have something slightly different. We have the energy being greater than the potential, What that means is that our Schrödinger equation is going to look like a second partial derivative of psi being equal to some negative number times psi. The way I'm going to define this, the constants that I'm going to define in this region, will make it look like the second partial derivative of psi is equal to, and I will call this constant minus L squared psi, where L squared now is E plus V naught. The potential in this region is minus V naught in this region. E plus V naught 2m over h bar squared. That's the constant we get under these circumstances. And this is our Schrödinger equation. Second partial derivative gives you minus some number squared times the wave function itself. You know the solution in this region is going to look like psi of x is equal to c sine Lx plus d cosine Lx. We can't really say anything more about this region because both sines and cosines obey this partial differential equation and are normalizable. So we don't know anything about whether we have c or d yet. We'll come back to that in a moment. Our third region here for x greater than a looks very much like our first region for x less than negative a, and the answers you're going to get are the same. The general solution, defining things exactly the same as we did here, is going to give us psi of x is equal to f e to the minus kx plus g e to the kx. Where now, if we want things to be normalizable, we have to say g is equal to 0, since e to the kx is going to blow up as x goes to positive infinity. Our overall solutions then in this region are going to look like f e to the minus kx. This is our general solution for normalizable bound states for this finite square wall potential. The next step I'm going to make requires you to think back to an activity we did earlier. The activity was to consider what we knew about the solutions to the time-independent Schrödinger equation for a potential that was even. If I go back a slide, our potential here is very much even. V of x is equal to V of minus x for all x's. We have an even potential here, we have those results. And one of those results was that if we had an even potential, we could write the wave function as either being even or odd. So, knowing how the Schrödinger equation behaves here for this even potential, we have some freedom. We can choose our wave function to be either even or odd, and that allows us to make some relationships between these constants. We have b, c, d, and f, and k being our unknowns. And we're not going to get enough boundary conditions unless we make some additional statements. So the first thing I'm going to consider is what if psi is even? We expect our lowest energy state, going back a slide, to look something like this. This would also be an even function, so if we're going to consider even psi, we should be able to find our lowest energy state. By combining these general solutions, we should be able to, well, come up with relations that give us not only the behavior on the boundaries between these regions, but also enforce the even nature of psi. So what does that look like? If we're going to have an even solution, our solution in the central region, psi of x, psi of x was equal to c sine Lx plus d cosine Lx. Well, if we're going to have an even function for psi, we can't have any sine term. So the first thing we know on the basis of it being even is that c is equal to 0. The second thing we know was that our solution on the left, the region for x less than minus a, psi of x was equal to b e to the kx. Whereas on our right-hand side, for x greater than a, we knew our solution psi of x was equal to f e to the minus kx. If we're going to have an even solution here, we have to have a relationship between these two cases. If x is large and positive versus, say, x is large and negative. If I'm going to have equality there, I have to have b equals f. So those are the conditions that we get from assuming that our wave function is even. We'll assume the wave function is odd later and see what other conditions we get. But for now, you know what your functions look like. You have these relationships between c being equal to 0 and b being equal to f coming from the wave function being even. Let's see what our boundary conditions can tell us. We have two boundary conditions. One is that psi is continuous. What that tells us, for instance, if I look at the boundary here between the central region and the x greater than a region, is that if I plug in the boundary, x equals a, here, for x in this equation and for x in this equation, I have to get the same answer. So that tells us that f e to the minus ka is equal to d cosine LA. The other boundary condition we have is that the first partial derivative of psi with respect to x is also continuous. What that tells us is we can take the first partial derivatives of these things, and they will also, and plug in the value x equals a, for instance, and that will also give us an equality. So if I take the first partial derivative of this with respect to x, I'm going to bring down a minus k, and I'll get minus k f e to the minus ka when I plug in x equals a. The right-hand side of my equality then comes from evaluating the first derivative of this expression at x equals a. And what you get for that, when you take the first derivative, you're going to pull out the L, essentially, and we will have the derivative of cosine being minus sine. I'll have a minus L d sine LA. There's still quite a few unknowns. I still have f, I still have d, I still have k. But one nice feature of this is that I can eliminate a lot of these unknowns by dividing these equations by each other. So I'm going to do that. I'm going to divide the second equation by the first. And when you get that, you do that division, you get minus k. The f e to the minus ka cancels out in the division. I've got a minus L here, and the d's cancel out. And I've got sine LA over cosine LA, which is the tangent of LA. So the equation that we have as a result of applying our boundary conditions is minus k is L times the tangent of LA, where, just for the sake of completeness, k is defined to be the square root of minus 2me over h bar squared. Most of the time I brought the h bar squared out of the square root. And L is defined as the square root of e plus v naught 2m over h bar squared. The constants have the identical units, and they relate the energy of the wave function to the potential. What we're interested in now is how to solve that equation. And it's a doozy. The definitions we're working with are k squared is minus 2me over h bar squared. L squared is equal to 2m over h bar squared e plus v naught. And the equation we're trying to solve is essentially k over L equals tan of LA, the tangent of LA. If you make some additional definitions, you can actually make some nice transformations. The first definition is that I'm going to call z LA, the argument of my tangent here. I'm going to call z. What I have for this, if I substitute in the definitions of L and L in this expression, z squared is equal to 2ma squared over h bar squared e plus v naught. Where, keep in mind, e here is a negative number that has smaller magnitude than v naught. If you figure out what k over L is here, substituting in the definitions of k and L, you get the square root of minus 2me over h bar squared divided by essentially what appears in the denominator, the definition of L and the definition of Z are very similar. The only difference is the a squared here. Essentially, this is z squared over a squared. If you go back, manipulate your expression for Z to solve for the energy, substitute in for the energy in the numerator here, what you end up finding after doing some algebra is that this is equal to defining a new constant z naught squared over z squared minus 1, where z naught, that new constant squared, is defined to be 2m a squared v0 over h bar squared. That means the equation that we're actually working with, we haven't really made that much progress towards solving it, but we have transformed it into a form that's easier to reason about. We have the tangent of z is equal to the square root of z naught squared over z squared minus 1. Keep that equation in the back of your mind. We'll come back to it in a moment. First of all, to check your understanding, I want you to work through the steps that lead to solutions for odd psi of x. If psi of x is odd, you can go through exactly the same reasoning that we went through over the last two slides to figure out what the odd solutions look like, what the constants have to be in our general solutions to enforce that psi is odd, and what the boundary conditions then give us for the continuity of psi and for the continuity of the first derivative of psi. What you should end up with at the end of this is an expression that looks very much like the expression we got on the last slide. What we got there was k equals L tan LA. For the odd solutions, you get k equals minus L cotangent of LA. These are, unfortunately, transcendental equations that don't have a particularly nice solution. There's nothing that we can really do other than solve these things numerically. What's nice about this is that I can solve it graphically. For instance, here is a simulation of what, or a plot of these solutions. I'm plotting the tangent, I'm plotting minus the cotangent, and I'm plotting the right-hand side of that equation, the z naught squared over z squared minus 1, all square rooted. If I plot the left-hand side versus z, and the right-hand side versus z, and I have intersections, that means that I have a solution. So the red curve here is what I get for the tangent. That was what I got for my even solutions. The green curves here, this is minus cotangent. That's what I got for the odd solutions. And the blue curve is the right-hand side. I have a slider here that I can use to tune the effective depth and width of the potential well. Small values of this slider refer to small values of the depth and or narrow values for the width. And if I have a small value here, my right-hand side, the blue curve, only intersects a single branch of the red curve. The red curve is tangent, which is what we got from our even assumption. So if we assume that psi is even here, we get an intersection. That means the only solution we have for this particular value of our effective width is, well, right here. It means we have only a single solution, and it's even. And this is the solution that we drew back at the beginning when we were trying to figure out what this solution might look like. If I increase the value of this slider, I'm effectively making the well deeper and or wider, and you pick up a second intersection, this time with the green curve. That's referencing cotangent, which is what we got when we assumed that the wave function was odd. So if I keep increasing the slider here, you can see what happens. This blue curve migrates to the right, gradually picking up more and more solutions. Here we've picked up a second even solution for a total of 3 total solutions, even, odd, and even. Here we pick up another green solution. And if I go all the way to the end here, this is just the end of my slider. There's nothing to prevent me from making the well deeper and deeper and deeper, wider and wider and wider. But for this particular value of that slider, this is essentially the value of z naught. We have 6 solutions. A lowest energy even solution, next highest odd, next highest even, then odd, then even, then odd, for a total of 6 bound state solutions for this particular well. So graphically, we can get a feel for how many bound states there are at a particular energy level. I can go and plug in the particular values of the depth and the width and the mass of the particle and Planck's constant and figure out, oh, in this case I have 4 bound states, 2 even and 2 odd. A couple of limiting cases are especially interesting here. First of all, we expect that if we have a very wide, deep well, we should get something similar to what we had for the infinite square well. Going back to my slider animation on Sage, for instance, if I make my effective width and depth of the well as large as possible, you can see what happens. The blue curve migrates to the right, and it's going to keep sort of migrating to the right as I make the well deeper and deeper and deeper. So these intersection points here, where I have my solutions for z, are going to become closer and closer and closer to these half integer multiples of pi. This first intersection is actually quite close already, but if I make the well infinitely deep, it's going to get even closer and closer and closer to pi over 2. Likewise for this, we'll become closer to pi. This intersection will become closer to 3 pi over 2, etc. So, if I have z naught large, you get many bound states, and they occur at values of that z parameter equal to n pi over 2, where n is now 1, 2, 3, going up to infinity. This is, of course, a very, very limiting case. But if you substitute in what we knew for our value of z, you can find what this gives you is that e sub n plus v naught is equal to h bar squared n squared pi squared over 4, I'll write it this way, 4 times 2m a squared. This looks very familiar. The right-hand side here is the formula for an infinite square well with width 2a. It's not the infinite square well formula exactly because we have this additional factor of 4, but otherwise it looks very similar. The left-hand side here, the energy of the nth state plus v naught. The energy of the nth state now, keep in mind, we're defining the potential well relative to 0 now. So if this is v of x is equal to 0, and this is minus v naught, what we're looking at here is the distance between the bottom of the potential well and the energy level. So this is essentially the energy level relative to the bottom of the well. Looks exactly like what we got for our infinite square well. So this is good. The other limiting case I'd like to consider is a shallow, narrow well. What this looks like back in our slider case is if I move the slider all the way to the left, I'm making the well very narrow. You can see the blue curve for my right-hand side for very small values of z naught is going to bring this all the way effectively down to 0. But we always do have that lowest energy state. We will only have one bound state, but we will always have one bound state. And it's going to be even. And that's more or less what we drew back at the beginning. That was our potential, and our wave function looked something like that. You can always have wave functions that look like this, no matter how shallow and narrow your potential well is. So those are our limiting cases. We can reproduce our infinite square well results, and we always have at least one bound state. But overall, the actual shapes of these and the actual energy levels they have are difficult to calculate. The only way we were able to make any progress is by doing things graphically. That concludes our description of the bound states for the finite square well. The bound states for the finite square well potential are discussed in another lecture. The subject of this lecture is the scattering states for the finite square well, which can be derived in a very similar way. The overall context is our finite square well potential, a potential v of x that's defined to be 0 for x less than minus a, 0 for x greater than a, and a constant minus v naught for x is in between minus a and a. So this is an even potential, and we exploited that fact when we were discussing the bound states, states where the energy is negative, to figure out what those states look like. And the lowest energy bound state that we found ended up looking something like this. smoothly joining the axis as x becomes large and negative, smoothly joining the axis for x becomes large and positive, and a smooth curve in between minus a and a inside the well. We found this by examining the general solution for regions less than minus a, between minus a, and greater than a, and smoothly matching those piecewise defined solutions together with the boundary conditions for the Schrödinger equation. We're going to take a very similar approach here, except instead this time we seek scattering state solutions, where the energy E is everywhere above the potential, and as a result our solution can extend all the way from minus infinity to plus infinity. The solutions that we get will end up looking a little something like this, but we'll see what they look like momentarily. Given this potential, we're looking at three distinct regions, and we're trying to solve our Schrödinger equation over those regions. Our Schrödinger equation, as always, is minus h bar squared over 2m second derivative of psi with respect to x plus v of x psi is equal to e times psi. Now we know away from our discontinuities, v of x is going to be a constant, so we expect the overall properties of this solution to be relatively straightforward. And indeed they are. Our three regions are divided by x equals minus a and x equals a. For x's less than minus a, our potential here is going to be defined to be 0, and our Schrödinger equation then simplifies to something of the form second partial derivative of psi with respect to x is equal to minus k squared psi, where k is defined as, for instance, in the case of the free particle, as 2me over h bar squared. K squared is 2me over h bar squared. We know the solution to this case for the free particle gave us traveling waves, and we're going to reuse that form of our solution here. We'll have psi being equal to a e to the I kx plus b e to the minus I kx. Traveling waves moving to the right and traveling waves moving to the left. Of course, nothing is traveling about this now, since we're just looking at solutions to the time-independent Schrödinger equation. But if you, as before, add the time dependence to these solutions, you find that they are indeed traveling waves. That was for the region where x is less than minus a. The region where x is greater than minus a is going to give us something very similar. It's going to give us an exactly identical Schrödinger equation, and it's going to give us exactly identical solutions, except we'll be working with slightly different constants. Our wave function psi is going to be given by, in this case I'll call it f e to the I kx plus g e to the minus I kx. Now I've used different constants for f and g, but the same constant for k, since overall we're trying to solve the same Schrödinger equation, so we have effectively the same value for e, and therefore the same value for k, as defined in terms of 2me over h bar squared. For the region in between minus a and plus a, we're going to have a slightly different Schrödinger equation. It's going to give us essentially the same sorts of solution though, but I'm going to write them slightly differently. Our overall Schrödinger equation will become, as before, the second derivative of psi is equal to minus some constant times psi, but the constant is going to be different. The constant, instead of being 2me over h bar, is going to be 2m over h bar squared times e minus v naught, but since, e minus v of x, let me step this out a little bit, e minus v of x, since v of x in the region between minus a and a is minus v naught, this is effectively e plus v naught. So we have our constants here, and in the case of these solutions, we could easily write them in terms of traveling waves with L instead of K, but it's actually slightly easier here to write them instead in terms of sines and cosines. This is just as general a solution, but let's write psi in this regime as c times the sine of Lx plus d times the cosine of Lx. Apologies for being messy here. These are then our three general solutions. We can call them psi 1, psi 2, and psi 3, if you like. But these are general solutions to the Schrödinger equation, the time-independent Schrödinger equation, for these three regions. The next step is to mesh these solutions together with our boundary conditions. And we had two boundary conditions, and if you're unfamiliar with the boundary conditions that we'll be using under these circumstances, I suggest you go back and examine the lecture on boundary conditions. The first of our boundary conditions was that the wave function is continuous, and the second was that the first derivative of the wave function is continuous. And there are sound physical reasons that that has to be the case. For instance, if the wave function itself is discontinuous, the expectation value for the kinetic energy of the wave function diverges to infinity and cannot be a physical state. But, considering the boundary at x equals minus a, ensuring that the boundary condition holds means meshing the value of this wave function at minus a and the value of this wave function at minus a. Excuse me. So let's go ahead and plug that in. Our boundary condition at minus a here is going to give us a e to the minus I kx plus b e to the I kx, oh, sorry, not x, we're plugging in for x, minus I ka, and then b e to the I ka, since I'm substituting in minus a for x. That's what I get for this region. That has to be equal to what I get for this region, which in this case I will write as minus c sine La plus d cosine La. Now if I substitute in minus a for x here, I would actually get the sign of minus La, but since sine is an odd function, I'm pulling the minus sign out front and writing this as minus c times the sine of La, just to keep the arguments inside all of the trig functions consistent. So this is our boundary condition for the continuity of psi. We have another boundary condition for the first derivative of psi, and you can write that down more or less just as easily by noting that in either of these cases, taking the first derivative with respect to x is going to bring down an ik. So we'll end up with ik times the quantity a e to the minus I ka plus b e to the I ka, and I've screwed up the minus signs already. Since the sign here is going to bring down a minus ik, when I factor out the ik, I'll still be left with the minus sign. So that's our first derivative of the wave function in this region. And if we're going to ensure continuity of the first derivative, we must also equal the first derivative of this wave function evaluated at the boundary. Taking the first derivative of sine and of cosine is going to pull out an L, so I'm going to have something that looks similar. I'm going to have L times a quantity, then the derivative of sine is cosine, c cosine La, and the derivative of cosine is minus sine. So I'm going to have minus d sine, and I'm evaluating it at minus La again, which I'm going to use to cancel out this minus sign. Sine of minus an argument is minus the sign of the argument, so I have two minus signs, and I end up with a plus overall. So these are our boundary conditions at x equals minus a. We get very similar expressions for our boundary conditions at plus a, but before I write them down, I'm going to make an additional simplification. Since what we're considering here are scattering states, for instance, in our consideration of the scattering of scattering states off of a delta function potential, we had a wave incident from the left, a wave bouncing back to the left, and we had a wave that was transmitted through. That was for a single potential. If we have some potential well, we're still probably interested in the same sort of process. A wave incident from the left, a wave scattering back to the left, and a wave transmitted through to the right. We're probably not so concerned with the wave coming in from the right, so I'm going to get rid of that one, and that amounts to setting g equal to 0 for our general solution in this regime. So we're no longer working with a fully general solution, but we have one fewer unknown to work with since we've gotten rid of g, which simplifies the algebra quite a lot. Makes it solvable, in fact. So, going through the same procedure we did at minus a, instead evaluating the wave function and its first derivative at a, the expressions we get are c sine La plus d cosine LA is equal to F e to the I k a. That's from just continuity, plugging in x equals a into this expression and setting it equal to plugging x equals a into this expression. Our first derivative, again, by taking the first derivative and repeating the process, gives you L times C times the cosine of LA minus now D times the sine of LA. We have a minus sign here because now we get the minus sign from taking the derivative of cosine, and we're substituting in plus a, so what I did to get a plus sign here no longer works. I can't factor a minus sign out. That's our left-hand side, and it's going to be equal to, first derivative of this brings down an ik, as before, ik f e to the I k a. So those are our general boundary conditions, and we have essentially 5 equations and 4 unknowns here. We have a, b, c, d, f, and k, all being unknown. K is determined entirely by the energy, and since what we're working with here are scattering states, we can treat the energy as something that we, the experimenters, control. But we still have these 4 unknowns, a, b, c, d, and f. Sorry, yes, 5 unknowns, a, b, c, d, and f, to take care of. As before, we can express reflection and transmission coefficients, in terms of these boundary condition expressions. The overall procedure is to essentially solve this system. Use these 2 equations to eliminate C and D in these equations, and what we'll be left with then is equations involving A and F. Sorry, A, B, and F. I always forget about B. By using these 2 equations, you can eliminate B and just get an equation with A and F. These are the same sorts of operations you are familiar with from solving systems of equations. What you end up with, for instance, solving for F in terms of A, is messy, unfortunately, but F comes out to be equal to e to the 2ika times capital A all over cosine of 2LA minus I k squared plus L squared over 2KL, and the I here, to make it clear, is outside. And this term is multiplied by sine of 2LA. So this is what you would get from solving the system of equations, and it gives you F in terms of A. Now, as before, if we're interested in a transmission coefficient T, T is usually defined to be the magnitude squared of F divided by the magnitude squared of A. The amplitude of the outgoing wave divided by the amplitude of the incoming wave. If we don't really care about the relative phases of those 2 waves, the transmission coefficient T encapsulates all the information that we could want. If you make this manipulation, dividing by A to get it over on the left-hand side, taking the squared absolute magnitude of this rather ugly expression, what you get for T is 1 over 1 plus V naught squared, your potential well depth, over 4E times E plus V naught times sine squared of 2A over H bar square root of 2ME plus V naught. Close parentheses, close my sign, everything still in the denominator. This is your expression for the transmission coefficient that you get by solving the system of equations and making the appropriate manipulations, finding absolute magnitudes and squaring them and the like. What this transmission coefficient actually looks like, as a function now of the energy of the incident particle, is a little strange. For very low energy incident particles, you get very low transmission. This is a little strange. A particle with low energy coming in towards a potential well is not likely to be transmitted. This is unlike the classical case where a cart rolling towards a dip picks up speed and then loses it again as it climbs the hill on the other side. It's unlikely to be reflected. In the classical case, you would never have any reflection from a potential well. In this case, however, we do have reflection because we have less than perfect transmission, and as before, we need r plus t equal to 1. As the energy of the particle increases, the probability of transmission, the squared amplitude of the wave function that passes the well, increases until it reaches 100%. That's a little strange. We have perfect transmission here. Zero reflection. What's even stranger about this transmission coefficient is that as the energy continues to increase, we stop having perfect transmission, actually go back down to quite a poor level of transmission depending on the well, on the depth and on the width of the well and the mass of the particle and the energy with which it's entering. As the energy increases, we come back again towards perfect transmission. Energy continues to increase, we lose our perfect transmission. Again we get perfect transmission, and again, etc. So, our transmission coefficient actually has some interesting properties here, and you can think about this as analogous to, for instance, anti-reflection coating in optics. If you have a lens and you don't want any reflections, you can think of putting a coating on the lens that results in perfect transmission for the particular energies of incident particles, for instance, the particular wavelengths of light that you're interested in. So there's some interesting properties here, and it all came as a result of looking at the general solutions to the Schrödinger equation and applying boundary conditions to mesh those solutions together, and then manipulating those boundary conditions. I have not actually written what the solutions to the time-independent Schrödinger equation are, what these traveling wave states that come in from the left mesh with solutions in the well and go off to the right. I haven't written what those solutions actually look like, but I have described properties here, for instance, of the solutions. This is characteristic of the sorts of calculations you want to do in quantum mechanics. If you don't have to work with the wave function itself, avoid it, because wave functions tend to be difficult and don't give you perfect information anyway. And the aggregate properties, things like the transmission coefficient in this case, can in some cases be derived without knowledge of the full details of the wave function. That's about it. To check your understanding, go back and look at that definition of the transmission coefficient and figure out what values the energy has where we get zero reflection. Those perfect transmission values have a nice interpretation in terms of the behavior of the infinite square well, so look at those energies and figure out where they happen in the context of the energies of infinite square well states. Linear algebra is very useful for quantum mechanics. We've already used a lot of the notation and terminology of linear algebra when we say, for instance, that two wave functions are orthogonal to each other. But quantum mechanics puts its own spin on things. In part, for instance, because we're not dealing with, say, three-dimensional Cartesian coordinates. We're dealing with a complex vector space that describes the state of a physical system. So dealing with complex numbers and dealing with vector spaces in a more general way is very useful, especially as we move away from simply solving the Schrödinger equation, but to manipulating solutions to the Schrödinger equation to infer the properties of physical systems. So, linear algebra will be useful in the coming chapters. To justify why this is useful, I'm going to make a couple of analogies. There are some things that we can say on the basis of vectors. We have vectors, A. We can make dot products between two vectors. We can express a vector A in, say, Cartesian coordinates, ax x hat plus ay y hat plus az z hat. We can also express some vector A in a different coordinate system. I'll call it a sub alpha, not x hat, alpha hat plus a beta, beta hat plus a gamma, gamma hat. Where now the hatted vectors here are unit vectors, and the numbers ax, ay, az, A alpha, A beta, and A gamma are simply components. They're simply numbers. If these x, y, and z, alpha, beta, and gamma represent different coordinate systems, we can still say that this is the same geometrical object, A. The vector A is not changed by expressing it in different coordinate systems. It exists independent of any coordinate system. And of course, we can also take dot products of unit vectors with themselves and get 1. Quantum mechanically speaking, each of these expressions in terms of vectors has an analog. The vector A, that's what we've been talking about so far as, say, psi of x. That's the state of the physical system, the wave function. Taking the dot product of two vectors, that's our integral from minus infinity of, say, psi sub a star of x times psi sub b star of x integral dx. Expressing a vector in terms of one coordinate system versus in terms of another coordinate system is essentially the difference between looking at the state of the system as the wave function psi of x versus the wave function in momentum space, the wave function phi of k, which we got by taking Fourier transforms back when we considered the free particle. Finally, taking the dot product of a unit vector with itself is like saying the integral from minus infinity to infinity, back with our expression of the dot product, of psi star psi dx is equal to 1. That's our normalization condition. Essentially, the analogy between vector operations and the wave function, given these particular definitions of something like the dot product, is a good analogy, and in fact, it's a mathematical identity. You can think of, for instance, the dot product as adding up similar components, like the x component of A multiplied by the x component of B plus the product of the y components and the product of the z components. Looking at it in terms of the wave function, here we're taking the component of the wave function at some position x, multiplying it by the component of some other wave function at the same position, repeating that over all different positions, and adding up all of those different effective components, position components of the wave function. So there are analogies between linear algebra and quantum mechanics, and they actually end up being very useful. Quantum mechanics, as I mentioned, puts its own spin on things, and just for the sake of being able to use the actual notation that people who study quantum mechanics use, instead of writing a vector A with an arrow on top of it, we write it like this, with a line on the left and an angle bracket on the right. This helps us to distinguish what's a vector from what's a scalar. It also helps to distinguish us from what's been complex conjugated to what's not been complex conjugated. And just staring at this slide, this should not be psi b star. This should just be psi b. Apologies for the error. Keeping track of what's complex conjugated is obviously rather difficult because I've just made a mistake doing it. But keeping track of what's complex conjugated, we do with this notation by writing complex conjugated vectors essentially the opposite direction. Now, being somewhat punny, the physicists that invented this notation decided to call it bracket notation. And being physicists, they decided that this would be called bra and this would be called ket. So if you see something like this written, you should read it as either the vector A or ket A, whereas this would be read as bra A, or the vector A complex conjugated. You can think of these in terms of the wave function as this representing psi and this representing psi star, and we'll come back to what that notation means in the context of inner products in a few slides. But for now, this is the notation that I'm going to be using to represent vectors in quantum mechanics, where now the vector is a more general thing than just something in, say, three-dimensional Cartesian coordinates. We're talking about something even more general than the wave function. It represents the state of a physical system, independent of any coordinate system. So it's not psi of x. It's the state of the system, which can be represented either by psi of x or phi of k, or an infinite sum of stationary states to the solutions, stationary state solutions to the Schrödinger equation. They're all different representations of the same physical state, and that physical state is what we mean by writing something like ket A. So that's the overall analogy, and that's the notation. Just to very briefly review some of the basic properties of vectors, we have vector addition. We can say vector alpha plus vector beta is equal to some vector gamma, which of course is also equal to the vector beta plus the vector alpha. Addition is commutative, and addition of two vectors gives you another vector. We of course have a zero vector. If we take some vector alpha and we add the zero vector to it, we just get alpha back. We have scalar multiplication. I can write something like a times the vector alpha and get something which I'll call the vector gamma temporarily, where gamma is just some vector that essentially points in the same direction as a but is only slightly longer or shorter, having been scaled by a, hence the term scalar. This scalar multiplication is distributive. I can write some scalar a times vector alpha plus vector beta as alpha times vector a, sorry, getting my notation mixed up, a times vector alpha plus a times vector beta. Or alternatively, I can look at a plus b times some vector alpha as a times the vector alpha plus b times the vector alpha. So scalar multiplication distributes across addition versus of vectors and across addition of scalars. Scalar multiplication is also associative, of course. I can look at a, b times the vector alpha as either a times, pardon my notation, as either a times b vector alpha, or b times a vector alpha, or as ab vector alpha. These are all equivalent. Scalar multiplication commutes and is associative. I already mentioned the additive identity here. There's a multiplicative identity as well. I can multiply a vector alpha by the scalar 1 and just get the vector alpha back. But those are our basic properties. Hopefully this is familiar. Either you can understand it from studies of linear algebra in general, or just by analogy with the day-to-day use of vectors in physics. Moving beyond the basic structure, one nice feature of vectors in linear algebra is that we can make linear combinations of them. For instance, if I have some vector a alpha plus scalar b vector beta plus scalar c vector gamma plus etc., I have a combination of vectors, each multiplied by scalars and all added together. This brings to mind a couple of useful concepts. First of all, linear independence. If I can write alpha is equal to, say, a times some vector beta plus c times some vector gamma, then you say this set, alpha, beta, and gamma, is not linearly independent. If, however, I cannot write alpha as a sum of beta and gamma multiplied by appropriate scalars, if there is no choice of alpha and a and c, such that I can make a sum of beta and gamma that equals alpha, then we have a linearly independent set. Alpha, beta, and gamma would be considered linearly independent, or alpha would be considered linearly independent of beta and gamma if it cannot be made by a linear combination of beta and gamma. If you have a bunch of vectors with which you can use to construct other vectors, you'll never get anything that's linearly independent from those vectors, but you can get vectors that are not in your original set. For instance, suppose I have some set of vectors xi. If I can write, let's say, my vector alpha as a sum ci xi, where I goes over the range of all of my vectors in this set, I've expressed alpha in terms of xi. In this case, I would say I have expressed alpha in the basis of states, or a basis of vectors given by xi. This ci here is, in some sense, c sub I is the x sub I component of the vector alpha. So if I have a set like this that I can use to express other vectors, you can describe that set as being a basis. Bases have other properties, and you can construct bases that have additional properties than this. Some bases are better than others, especially if you have a variety of purposes you want to accomplish. But the notion of a basis is that it is a set of vectors that can be used to construct other vectors. And the set of vectors that can be constructed from a basis, the space of vectors that can be constructed from a basis, is the space spanned by the basis. So, for instance, let me write, if every alpha in some space, the space that we're interested in, can be written like this: alpha equals sum over I c sub I times ket x sub I. We say the set of basis vectors x sub I spans the space we're interested in. For instance, the x, y, and z unit vectors in Cartesian three-dimensional coordinates spans all of three-dimensional space, three-dimensional Cartesian space. So if I have a set of basis vectors that spans a space, the dimension of the space is the minimum size of a basis. So if I have, say, in 2 dimensions, in the plane of this sheet of paper, if I have a vector that points in that direction, and a vector that points in that direction, and a vector that points in that direction, all in the plane of the screen here, I have 3 vectors, but they are not linearly independent, since I could construct this vector from a combination of these 2 vectors, or in any other order. Any of these vectors can be constructed by a superposition, by a linear combination of the other 2. And I have 3 vectors, so you would think I have a 3-dimensional space, but it's not the minimum size of the basis. I could say, drop this vector, just work with these 2, and still have a set of vectors that I could use to express any vector that lies in the plane of the monitor. So that's a little bit about superposition and linear combinations and some of the terminology that we'll use to describe what happens with them. The next major topic is inner products. The inner product in quantum mechanics, the inner product between 2 vectors is written like this. I'll keep using my Greek letters. Bra alpha ket beta. And you can think of this a little bit like A dot B, working with conventional vectors, but it's different. And it's different in a couple of ways. First of all, we're working with complex conjugates now. So if I wrote alpha beta inner product, and I compared that with beta alpha, I would have to take the complex conjugate. If I exchange the order of the 2 vectors in an inner product in this complex number space, you have to take the complex conjugate of the result. We do have some familiar results, though. For instance, if I take alpha and dot it with itself, take the inner product of the vector alpha with the vector alpha, you get a real number, and it's going to be greater than or equal to 0. You also know, and this should hopefully not surprise you, that if alpha dotted with itself, the inner product of alpha with itself, equals 0, if and only if alpha is equal to the 0 vector. It's very common to write the 0 vector as just 0. It's usually reasonably clear from the context whether you're talking about a 0 vector or a 0 scalar. This is a little bit like writing 0 without units. We do that a lot in physics. We'll say, how tall, how long is this? Well, 0. You wouldn't say 0 meters or 0 nanometers or 0 kilometers, because it doesn't matter what the unit is if it's 0. It doesn't really matter if we have vector 0 or scalar 0, it's still 0. We also have some familiar concepts. For instance, if I write alpha inner product with beta, and that equals 0, we say these 2 vectors, or states, are orthogonal If we have a set of states, xi, such that xi dotted with, or inner product with, xj is equal to the Kronecker delta ij, we say we have an orthonormal set. This xi set is orthonormal. For instance, if I write x, y, z as unit vectors, they form an orthonormal basis for three-dimensional Cartesian coordinates. Now, note that in all of this, you might think, well, I'm taking the inner product between two vectors. I know how to do that. I figure out what the x components and the y components and the z components are, I multiply them together, and I sum them up. But I want you to start divorcing in your mind the notion of something that looks like this from something that looks like this. Because we don't necessarily have components that we want to consider. We have physical states. And it turns out the mathematics of linear algebra can tell us about the properties of these states and how they interact without actually expressing them in any basis. Of course, we can do a lot of things when we do express them in a basis as well, but the vectors themselves can live without the basis. Having defined an inner product, it's also useful to define a norm, and this is occasionally written as, like, if I write two lines with an alpha in the middle of it. This is more or less defined to be alpha dot product with itself square rooted. Since the square root, or since the inner product of alpha with itself was defined to be a real number, positive real number, the square root of this is also a positive real number. This is our unit of, or our definition of length, if you want to think about it that way. And if we have some vector alpha with norm 1, we say it's normalized. It's a unit vector. A normalized state. Your normalized state is a slightly more useful term than saying it's a unit state. You don't hear unit state, though you would hear unit vector. You will also hear normalized vector. So normalized is sort of a more general term. Finally, now while I have said that vectors can live without the components, it is useful to express things in terms of components many times. So if I have a basis of unit vectors, an orthonormal basis set that spans the space that I'm interested in this case, three-dimensional space, I can write the vector alpha as alpha x times, keep wanting to write x hat, times the vector x plus, alpha y times the vector y plus alpha z times the vector z. Likewise, for some vector beta is beta x vector x plus beta y vector y plus beta z vector z. And I can write out things like the inner product alpha beta, and it looks pretty much the way you would expect. It looks like alpha x star beta x plus alpha y star beta y plus alpha z star beta z. You can also, of course, write the inner product of alpha with itself and get alpha x star alpha x plus alpha y star alpha y plus alpha z star alpha z, which you recognize as the squared magnitude of all of those components, all summed up together. Each of these components, incidentally, these alpha x, alpha y, alpha z, beta x, beta y, and beta z, can be found by taking inner products. Alpha x is defined more or less as x inner product with alpha. Likewise for alpha y, being defined as y, unit vector, unit bra, y, inner product with ket, alpha. And likewise for z. This is all in three-dimensional space, and we can actually work in higher dimensional spaces as well. Nothing here is really limited to 3 dimensions. If I have some set of orthonormal basis kets x sub I can write the vector alpha as the sum over I of some alpha sub I times x sub I, given suitable definitions for alpha sub I. In particular, alpha sub I is x sub I inner product with the vector alpha. And you can write out expressions for alpha inner product with beta. That's a sum over I of alpha sub I star beta sub I, or the inner product of alpha sub I with itself. Not alpha sub I. The inner product of vector alpha with itself is the sum over I of alpha sub I star alpha sub I. Total sum of all of the squared moduluses, whatever, of all of the components of alpha expressed in this basis. So that's a little bit about how linear algebra is expressed and some of the things that we can do with it. As an example, I would like to check your understanding with the Schwarz inequality. This is just an exercise in manipulating vectors, but the Schwarz inequality, and this is something that can be useful in quantum mechanics, what it states is that the inner product of some vector A with some vector B, squared magnitude, is always going to be less than or equal to the squared magnitude of A multiplied by the squared magnitude of B. So, inner product of A and B, squared magnitude, is always less than the inner product of A with itself and the inner product of B with itself. This is the squared norm of A and the squared norm of B. So your task is to check that this inequality holds for the two vectors given, where here x, y, and z is an orthonormal set that spans some three-dimensional space of interest. Note that I'm not necessarily talking about three-dimensional Cartesian space here, but it's a good analogy to keep in the back of your mind if you're having trouble imagining what these things should look like. Our whirlwind tour of linear algebra continues with linear transformations. Here, we'll write linear transformations with hats. For instance, t with a hat, capital letters especially, will be considered to be transformations. A linear transformation, quite simply, is a transformation that's linear. What it means for something to be linear is if I apply the transformation to A times the vector alpha plus B times the vector beta, I get A times the transformation t applied to the vector alpha plus b times t applied to the vector beta. If this sort of identity holds, the transformation you're working with is linear. It's difficult to work with transformations in general, so it's useful to consider what a transformation looks like if we have a vector in a particular basis. So suppose I have a set of basis vectors, x sub I. I'm not telling you how big this set of basis vectors is, but if we have our transformation applied to the basis vector x sub I, let's say x sub 1 in particular, that transformation applied to a basis vector will be given by another vector, which is in general going to be expressed as a sum of basis vectors. So x1 will be transformed into some number, which I'll write as t11 x1, vector x1, not xi, excuse me, tx1, plus some other number, t21 times the vector x2, plus t31 times the vector x3, etc., up to xn. If I have, say, x2, I get a similar expression, except I'm going to number things slightly differently. I'll say this is the t12 number, is the x1 component of the transformation applied to x2, plus, etc., t22 x2 plus t32 x3 plus, etc. So if I have some vector then, alpha, being expressed as a1 x1 plus a2 x2 plus a3 x3 plus, etc., up to xn, I can write that as a sum over, say, j equals 1 to n of aj times x sub j. And you can find these components, a sub j, the way we described in the last lecture. If I apply this transformation t hat to this vector alpha, I'm going to get a sum of sums. Essentially, the first thing that I'll get is this sum over j of aj, and then the transformation t hat applied to x sub j. But I know what the transformation t hat applied to x sub j looks like. It's going to look something like this. It's going to look like a sum over something I'll call I. But first I have my sum over j, then I have a sum over I, and I'm left with the aj as before. And then these sums, if I'm expressing them as sums, I'll end up with tij times x sub I. So this is just taking these summation expressions and substituting them in for the application of the operator of the transformation t hat to x sub j. You can exchange the order of summations here if you want to find out what the xith component is more straightforwardly. We'll do the sum over I first then, and then we have the sum over j of aj tij gives us the x sub ith component of the operator, the transformation t, applied to the vector alpha. I keep saying operator accidentally here. The connection with hat notation between our operators, for instance p hat in quantum mechanics, and the transformations I'm working with here, t hat, is not coincidental. We will see there's a connection in the linear algebra interpretation of quantum mechanics between operators and transformations. So what we've done here is we've expressed our transformation t hat in a basis, x sub I, with, say, n entries. So we have some n-dimensional space with n basis vectors, and we can express our operator, our transformation, in that basis. What we get is these numbers, t21, t11, etc. It's convenient to represent these numbers as a matrix, instead of just writing out t11, t12, etc. We can take our t hat, our transformation, and in a basis, we end up with numbers, tij. And it's useful to write those tij's in matrix form. Upper left we have t11, then t12, up to t1n. Second row we have t21, t22, up to t2n, going all the way down to tn1, and all the way over to tnn. So that's the structure, and that's how we write these things as matrices. The ijth component here, incidentally, can be found by consideration of the orthogonality of our basis vectors. Tij can be written as x sub I inner product with t, the operator, acting on the basis vector x sub j. So if I apply t to x sub j, we had expressions for that on the previous slide. We got a sum of the x sub j's running from 1 to n. And if we take the inner product using the orthogonality of the x sub I and x sub j basis vectors, we can pull out just the x sub ith component. And that will tell us what the number tij is. So if we have some way of acting with these operators, you have an effective way of finding what the components of your operator are, of your transformation, in the particular basis that you're working with, x sub I. So, in this matrix interpretation, the sums that we expressed on the previous page have a nice interpretation. If I apply the transformation t to the vector alpha, I can write that as, and I'm going to cheat and just copy paste this matrix acting on the vector alpha. If I express alpha in this basis, I could write alpha as alpha 1, alpha 2, up to alpha n as a column vector. And the sums that we expressed on the previous page are exactly the matrix vector product. So treating the vector in our basis as a column matrix, we can do this matrix vector product, this matrix product, And what you end up with is the representation of t hat acting on A in this basis. So these matrix vector products will be a useful way of manipulating vectors and matrices as they represent transformations and states in quantum mechanics. This transformations, of course, can also be combined with each other. You can have a transformation A hat and add a transformation B hat. This, if you imagine applying it to a vector, say alpha, is just going to give you A hat applied to alpha plus B hat applied to alpha. And if you're working with matrices, the A hat plus B hat represented as a matrix, if I want to know the ijth entry of the matrix that represents the sum of these two transformations, it's just going to be A ij plus B ij. The element by element sum of the two matrices treated separately. We can also write out the product of two transformations. For instance, if I have A hat, B hat acting on the vector alpha, you can think about this as the composition, A hat acting on B hat acting on alpha. But it turns out that in matrix representation, this is just the matrix vector matrix product. You can work out all of the sums necessary to figure out what this sort of expression actually looks like in terms of components, and what you get is the summation expression for the matrix product. So we can compose transformations applying one after the other by multiplying their matrices together, and we can apply a sum of two transformations by simply adding the elements of their matrices. So we're going to be working with matrices quite a lot. It helps to know some of the things that we can do with matrices. What are their properties? Well, some things that we can do with matrices. We can take the transpose. The transpose of a matrix, denoted by putting a twiddle over the top of the matrix. If I have some matrix Aij that I want to transpose, that is the ijth entry of the transpose of A is Aj, exchanging the order of the indices in our matrix. Essentially, this means taking an entry below the diagonal and swapping it for the identical entry above the diagonal, flipping the matrix across the diagonal. We say a matrix is symmetric if the transpose of the matrix is equal to the matrix. Essentially, taking the transpose does nothing. And we say a matrix is antisymmetric if taking the transpose gives you the matrix back with a minus sign, if taking the transpose flips the sign. Essentially, if all the entries above the diagonal are the same as the entries below the diagonal, but with a minus sign. We can also take the complex conjugate of a matrix, which we'll write as A star, using our complex conjugate notation, and that's relatively straightforward. If I have some matrix A star, and I want to know the ijth component, it's just Aij complex conjugated. Let me simplify my notation a little bit. If I have A star and I want to know the ijth entry, I have the complex conjugate of the ijth entry of A. It didn't really matter how I wrote that. To take the complex conjugate of a matrix, you take the complex conjugate of all the elements of the matrix. We describe then a matrix as real if the complex conjugate of the matrix is equal to the matrix, and imaginary if the complex conjugate of the matrix is equal to minus the matrix. If all the elements are real, you have a real matrix. If all the elements are imaginary, you have an imaginary matrix. Where things start to get interesting now is defining combinations of these operators. The Hermitian conjugate which is also sometimes called the adjoint of a matrix. And the notation here is A dagger. The daggers look much nicer in LaTeX, but this sort of A cross would be read as A dagger. And the Hermitian conjugate, A dagger, is defined to be the complex conjugate transpose of the matrix. Hermitian conjugates have an interpretation in terms of transformations and operators, which we'll come back to. But for now, we describe a matrix as Hermitian if the A dagger is equal to A. The Hermitian conjugate of the matrix is equal to the matrix. Or anti-Hermitian if the Hermitian conjugate is equal to minus the matrix. Coming back to our inner product, if we're representing states as vectors, if I have something like alpha, beta, the inner product, alpha, beta, I mentioned now that the alpha written as a bra as opposed to beta, which is written as a ket. The difference between bras and kets here is has something to do with the complex conjugate. If we're writing alpha and beta in a basis as vectors, the matrix product here, which is what we're working with, the dot product of the two vectors, can be written as alpha dagger as a matrix times beta. So alpha dagger, and I didn't really make that look like a dagger. To distinguish it from star, I need to elongate things a little bit. Alpha dagger times beta. The vector representation of alpha in a basis is, as it was in the previous page, a column matrix. Alpha dagger, then, the complex conjugate transpose, is going to be a row matrix. Beta, again, not being Hermitian conjugated, is going to be a column matrix. And I can take a row matrix and multiply it by a column matrix, and I'm just going to get a matrix with only one entry in it, a scalar, essentially. So that's how these sorts of properties work out. Transposing matrices, we'll talk about the symmetry of matrices, we'll talk about the Hermitian conjugates of matrices, Hermitian matrices versus anti-Hermitian matrices, and to close the loop a little bit back to what we talked about with inner products, Hermitian conjugates are what you need to convert your column matrix representation into a row matrix complex conjugate representation to actually end up with a sensible inner product of matrices in this complex number space. That's not all, though. We've got more matrix properties to work with. Back when we were talking about operators in quantum mechanics, we defined something called the commutator. We can define commutators in terms of matrices as well. And if I have some matrix A, the commutator with A with some matrix B is same as it was in operators, AB minus BA. Except now we're talking about the matrix product AB subtracting the matrix product BA. Matrix products are non-commutative, same as operators are non-commutative in quantum mechanics, and the connections are starting to become a little more clear. We can take the transpose of a product, AB, and if I have AB, the product, transposed, that's equal to B transposed times A transposed. So the transpose of the product is the product of the transposes, but in the opposite order. This follows over to Hermitian conjugates as well. If I have a matrix product AB that I want to take the Hermitian conjugate of, I get the Hermitian conjugate of B multiplied by the Hermitian conjugate of A. Just for the sake of clarifying notation, we also have a unit matrix, which is a matrix with ones down the main diagonal and zeros off the main diagonal. For instance, if I wanted to know the ijth entry of my identity matrix, it's the Kronecker delta, which we learned about earlier when we were talking about orthogonality. That's still not it. There are still more matrix properties. Things to mention that you need to remember. The inverse of a matrix, denoted A to the minus 1, is defined such that A to the minus 1 times A is equal to A times A to the minus 1 is equal to my identity matrix. If you can find an inverse like this, these products work out. There isn't always an inverse. You have an inverse if and only if the determinant of your matrix is non-zero. So you need to remember determinants, which I'll just write as det of A. Your determinant of A is not equal to 0. This inverse also behaves a little bit like the Hermitian conjugate in the transpose, in the sense that if I have some matrix AB inverse, it's the inverse of B times the inverse of A, which you can see pretty easily by thinking about what would it mean to take the inverse of AB. Well, I would have AB times its inverse has to give me the identity, and you have to reverse the order in order to make that happen, because then I could identify B times B inverse as the identity. Pull that out, essentially, since it's going to do nothing if it's sandwiched between two other matrices. And then A times A inverse would also give me the identity, and I'd just be left with the identity. One last property to mention, I think that's about it, yeah. Unitarity. We describe a matrix as unitary if the Hermitian conjugate of the matrix is the inverse of the matrix. So I can take this little horizontal line and push it a little bit to the left. No. Notationally speaking, there is a lot of things to keep track of here. We have a dagger, we have a star, we have a twiddle, we have a minus 1. We have the determinant of A. And they all interact in ways that you need to keep straight. But unitary matrices will play a special role in quantum mechanics. The last thing I want to mention in this lecture about transformations in matrices is how to change the basis of a matrix. So suppose I have some matrix A. That's if I'm going to express some operator A in a basis, let's say basis 1, I'll get the matrix A. If I want to express it in basis 2, I'll get some other matrix, which I'll write, say, A prime. Actually, no. Let's call it B. So B is the matrix that represents the transformation A hat, but in a different basis. If you want to think in 3 dimensions, for example, the transformation A maybe multiplies your x-coordinate by 2. Well, multiplying the x-coordinate by 2 in one basis is going to be different because, for instance, you could have another basis where the y-coordinate was the x-coordinate, and then it would have to multiply the y-coordinate by 2. So your matrix representation would be different. You can think about changing from basis 1 to basis 2. That's going to be yet another transformation. So say I have some transformation that goes from basis 1 to basis 2. That transformation I'm going to call S. So if S takes a vector from basis A, a vector expressed in basis 1, and re-expresses it in basis 2, I can use S to figure out what B is in terms of A. So the first thing you're going to have to acknowledge here is that A acts in basis 1. And if I want an expression for something acting in basis 2, I'm going to have to take my vector from basis 2 back to basis 1, allow A to act on it in basis 1, and then convert back to basis 2. And the way we write that is S times A inverse times, S times A times S inverse. If I'm allowing this to act on some vector alpha, I can think about S inverse as going from basis 2 to basis 1. So alpha in basis 2, this S inverse alpha is going to be alpha in basis 1. Now that alpha is expressed in basis 1, I can allow A to act on it. That will give me another vector also expressed in the basis where A operates, basis 1. Then I can use S to transform back to basis 2. So if I have a vector in basis 2, I can convert it to basis 1, allow A to act, and then transform back. Now we know how to compose products, or how to compose operators or transformations like this. This matrix is going to be our matrix B, our representation of the operator A in basis 2. So this is how change of basis works. If I have some transformation S that I can use to connect basis 1 to basis 2 and vice versa, then I can take a vector expressed in basis 2, express it in basis 1, allow A to act, and then transform back to basis 2. And if I just treat all three of those operations as matrices, you end up with a matrix product that gives you the representation B, which tells you how A acts in basis 2. So essentially B is equal to S times A, I know I keep writing an inverse there, times S inverse, for some S that connects the two bases together. So that's about it for matrices. To check your understanding, given this matrix and this vector, calculate these quantities. The Hermitian conjugate of A applied to B, and then the Hermitian conjugate of B left multiplied by the matrix A. And the final question is to figure out how X and Y are related to each other. So just to get you back in the swing of doing matrix operations and figuring out how matrix vector products work. This is the last major piece of our discussion of linear algebra, eigenvalues and eigenvectors. This is one of the really important pieces from the perspective of quantum mechanics. Over the past lectures, I've probably said eigenvalue or eigenvector or eigenstate without really thinking about it or noticing. So it's important to understand what these things are, and they will be used extensively throughout our discussion of the mathematical formalism of quantum mechanics. Essentially, what eigenvectors and eigenvalues are special vectors for a transformation. Suppose, for example, I have Cartesian free space, say x-coordinate, y-coordinate, z-coordinate, x-axis, y-axis, and z-axis. If I consider a transformation that is rotation about the z-axis, for instance, a vector here in the x, y plane would be rotated around, say, to point in some other direction, remaining in the xy plane. A vector that points along the z-axis would remain unchanged, whether it's pointing upwards or downwards. These vectors that are unchanged in a transformation have some special status, and it's not simply, for instance, the vector that points along the z-axis in a transformation like a rotation like this. You can think, for instance, suppose I have just 2 dimensions now, and consider a transformation that takes like a box shape like this and maps it to something that's skewed, stretched out in the x direction and smooshed over in the y direction. If I had a transformation like this, you can probably imagine what one of the vectors that remains unchanged would be. It points along the x-axis. And it's not going to remain unchanged, but it's going to be extended slightly. It's going to point in the same direction. As opposed to some other vector, which for instance points in, say, this direction, and it's going to be extended and shifted over. So the blue vector here is not unchanged. The orange vector, however, is essentially unchanged. It points in the same direction. There's actually another vector in this transformation that remains unchanged, and it points sort of off in this direction. That vector actually legitimately remains unchanged. It is neither extended nor contracted. You can think about this transformation as taking your x-coordinate and multiplying it by some value. The y-coordinate remains unchanged, but the x-coordinate also depends on the y value. The higher up you go, the further over you get shifted. And if you're lying along this vector, the fact that you get shifted over in x and the fact that you're along a line, you're essentially along a line where the amount that you have moved up in y counteracts the amount that you're shifted over in x, and you end up essentially back where you started. So these special vectors are called eigenvectors, from the German prefix eigen, which means self or proper. So these are the self values or the proper values of a transformation, the values that return to themselves in some sense. And the amount, for instance, by which this orange vector gets increased in length or decreased in length is the eigenvalue. More formally, what we're looking at are equations that involve transformations. So, as before, t hat will represent my transformation, and I will write vectors associated with the space that we are interested in as kets. in bracket notation. Your eigenvalue equation fundamentally then is your operator acting on your vector gives you some eigenvalue, lambda, times your original vector. So the action of your transformation is to return a scaled version of the vector that you started with. Since most of what we're going to be talking about in this lecture is what happens when we represent a transformation in a particular basis, you can think in terms of matrices. The matrix T acting on the vector A gives you back the eigenvalue lambda times the vector A. And we can rewrite this a little bit if you think about trying to bring the right-hand side over to the left-hand side. You would end up with T acting on A minus lambda multiplying A, lambda just being a scalar, not a matrix or a vector or anything. And if I want to factor A out of this expression, I can write this as the matrix T minus lambda times the identity matrix, all acting on A as a matrix. So this is going to be equal to 0, as is this. And this is the sort of equation that we're going to be considering when we talk about finding eigenvalues. So lambda is our eigenvalue, and A is our eigenvector. I haven't said why these things are interesting yet. Mostly they're interesting because they tell you what the core properties of the transformation are. These are sort of the most interesting facets of a transformation. And when it comes to quantum mechanics, we'll see that these things are actually very important. So bear with me while we go through some of the mathematical details. If what you're interested in doing is finding eigenvalues, the easiest way to think of it is in terms of that expression. We're working with a matrix equation, T minus lambda times the identity, multiplied by some vector, is equal to 0. You can imagine trying to solve this by standard techniques involving matrices. For instance, if I called this matrix A, I would have capital A acting on A is equal to 0. And I could solve this by left multiplying by the inverse of A. I can multiply by inverse of A over here and by inverse of A over here. The right-hand side, of course, is going to remain 0. The matrix A, no matter what it is, acting on the 0 vector, will give me 0. But on the right-hand side, I'll end up with the identity here, and I'll just end up with A equals 0. This was not particularly informative. It didn't tell us anything about A. The reason that we can have these vectors that are unchanged by transformations is that it's actually impossible to solve the equation like this. This doesn't work. And the reason this doesn't work is that if we have A not equal to 0, the only way this equation can have a solution is if the determinant of T minus lambda identity is equal to 0. So our actual equation to determine the existence and value of an eigenvalue is this equation. And that's what we're interested in. The determinant of the matrix T minus lambda times the identity equals 0. This is an equation that we can solve for lambda. And if we solve it for lambda, we'll find the eigenvalues. We won't find just one solution to this equation. We'll find many solutions. If this is an n by n matrix, this equation is an nth order polynomial in lambda. So if we have an nth order polynomial, we're working with complex numbers, we have n roots, so we have n eigenvalues. These eigenvalues are not necessarily distinct, but we should have n of them. So whatever the dimension of our space is, whatever the size of our matrix is, we should get that many eigenvalues. So the best way to see how solving this process actually works is to go through an example. So find the eigenvalues of this matrix, 1 minus I minus 1. There's some special structure to this matrix. If you recall back to when we were talking about the properties of matrices, if I take the transpose of this matrix and the complex conjugate, I find that I have my original matrix back. The I and minus I will exchange places, but then I will be exchanged for minus I again when I take the complex conjugate. So this is in fact a Hermitian matrix, and Hermitian matrices have some nice properties from their eigenvalues that we'll talk about more later. But for now, let's figure out what finding the eigenvalues actually looks like. we're looking for an equation of the form matrix A multiplied by some vector, and I'll just leave it as vector A, equals lambda times our vector A. And I told you that you could solve this by moving this over to the left-hand side and trying to solve for the determinant of your matrix under those circumstances being equal to 0. That's what's called the characteristic polynomial, the equation, the characteristic equation. The determinant of 1 minus lambda minus I minus 1 minus lambda is equal to 0. That's our characteristic equation. That's what we get when we rewrite this as A minus lambda times the identity matrix multiplied by A equals 0. And this matrix is what we're taking the determinant of. So you know how to find the determinant of a 2 by 2 matrix. It's just something that you can write down. It's 1 minus lambda, this term, times this term, which I'm going to write as minus 1 plus lambda. And then I subtract from that this term times this term, I times minus I. And that's all going to be equal to 0. If you expand this out, you end up with minus 1 minus lambda squared from these two terms, minus 1 from this equals 0. So the actual equation you have to solve in this case is pretty easy. Lambda squared equals 2. What that means is that our eigenvalues, lambda, are equal to plus or minus the square root of 2. So we have two eigenvalues, plus and minus the square root of 2. So we found our eigenvalues. What about our eigenvectors? The best way in general to solve for the eigenvectors is to go back to this equation, substitute in the value of the eigenvalue, and solve the system of linear equations that results. So let's see what happens when we do that. Given this is our original matrix, let's suppose we have just the eigenvalue root 2. Let's just work with finding the eigenvector associated with the eigenvalue square root of 2. Our linear system, as before, A times some vector A equals lambda times A, can be reduced to A minus lambda times the identity matrix times A equals to 0. So let's just write our system like this. We have our matrix A minus lambda, which we now know is the square root of 2. So when I substitute that in here, I get 1 minus the square root of 2 for my upper left element, minus I, unchanged, for my upper right element, I for my lower left element, again unchanged, and minus 1 minus the square root of 2 for my lower right element. This is my matrix, and it will be multiplied by some unknowns, say x and y. So I can expand out this matrix vector product and get a system of equations that I can solve. For the first equation, I get 1 minus the square root of 2 multiplied by x minus I, y, equals 0. For the second equation, I get I times x minus 1 plus the square root of 2, y, equals 0. And if, for instance, I rearrange this equation, which tells me that x is equal to minus 1 plus the square root of 2, y, minus I times 1 plus the square root of 2, y, and substitute this into this equation for x, what I end up with, and I'm writing it in the margins because you'll see this doesn't actually work, I end up with minus 1 minus the square root of 2 times 1 plus the square root of 2 times I, y, minus I, y, equals 0. And if you expand all this out, you find 0 equals 0. Effectively, I get IY minus IY equals 0. So it didn't actually tell me anything, but we knew that was going to happen because we set lambda such that the determinant of this matrix was 0. So this system of equations does not uniquely determine a solution. It does actually determine the direction. Essentially, these represent two parallel lines that are overlapping on top of each other, and the direction of those lines is interesting. And the easiest way to figure out what the eigenvectors is, then, is just to take one of these equations and substitute 1 in for x. And if you do that, you can just write down the vector more or less. You find that the vector is 1, and then solving a single one of these equations, substituting in 1 for x, you can see you're going to get something like minus iy, and then in the denominator you're going to get 1 minus root 2, and then in the denominator you're going to get minus I. You end up with I, say, root 2 minus 1. That's actually your eigenvector associated with the eigenvalue square root of 2 for lambda. If you repeat this procedure with lambda equals minus the square root of 2, our other eigenvalue, you get more or less the same sort of structure. Again, an algebraic system of equations that cannot be solved. It just ends up looking slightly different. And you have 1, and then minus I, 1 plus square root of 2. Sorry for writing so small here. But the overall procedure for finding eigenvectors, at least by hand, for small matrices like this, it is most easy to substitute in the eigenvalue that you found by solving the characteristic equation, setting the determinant for this matrix equal to 0 and solving for lambda, then getting a system of equations that is singular, and doing your best to solve the singular system of equations, substituting in a variable as needed. Given this discussion of eigenvalues and eigenvectors, it's useful to consider the concept of diagonalization. The eigenvalues have this special property where they are mapped back to themselves by your transformation. And it turns out that we can use these eigenvalues and eigenvectors to make a change of basis that converts your matrix into a diagonal matrix. This process is called diagonalization. To see how this can happen, consider I have some transformation A. I can express A in any basis, really, and I'll consider two bases, just any old basis, and then an eigenvector basis, where I mean finding the eigenvectors of the transformation A and using those eigenvectors as basis vectors. If I express the matrix, or the transformation A in any old basis, I'll just call that the matrix A, whereas in the eigenvector basis, I'll call that matrix A prime. Let's think about what A prime does. A prime, as any representation of this transformation will do, it will take an eigenvector alpha, and, sorry, I should write these as vectors, not kets. This transformation A prime will take a vector A and return lambda multiplied by the same vector, a scaled version of the original vector. If I consider what A prime actually looks like, and what A actually looks like, this eigenvalue equation will only be solved, suppose, say, I have A1 and eigenvalue 1, where lambda 1 is the eigenvalue, the first eigenvalue, and A1 is the associated eigenvector. In the eigenvalue basis, which is where we're expressing A prime, I'll just leave A prime blank for now. What does our eigenvector look like? Well, we're expressing an eigenvector in the eigenvector basis. So the eigenvector basis, if this is, say, two components, lambda 1 and lambda 2, lambda 1 and eigenvector 1 would constitute the first component. So I'll have some number here. I'll just call it, well, I'll just say 1. Whereas the component in the direction of the other eigenvector would be 0. We just have a single eigenvector here, and we have no contribution from any other eigenvectors. If I act with A prime on this, I have to get lambda times our original vector back. This also has to hold if I, again leaving A blank, use the other eigenvector. I have to get the same sort of equation, 0 lambda, where this now, let's say this is lambda 1 and this is lambda 2. First eigenvector, second eigenvector. So my first eigenvector, written in the eigenvector basis, is very simple. My second eigenvector, written in the eigenvector basis, is simple as well. And the matrix that works here has lambda 1 and lambda 2 on the diagonal, and zeros off the diagonal. Lambda 1, 0, 0, lambda 2. And you can see that this matrix works pretty well. And this matrix has the nice property that it's diagonal. It's much easier to work with diagonal matrices than non-diagonal matrices. So what we're looking for now, knowing that A prime is diagonal, if I express my transformation in an eigenvector basis, I need to make a change of basis. Typically, what you won't be given a transformation, you'll be given something like a matrix, and it won't be written in the right basis. So you need to make a change of basis. So we're looking for some change of basis that gives me A prime in terms of something, and I'll write it as S inverse times the original matrix that you're given times S. If you consider this acting on a vector in the eigenvector basis now, what S has to do is convert from the eigenvector basis to the basis of our original matrix A. So if I have a transformation that goes from my eigenvector basis to the basis of A, I can actually just straight write down that basis. And write down that transformation, that matrix. And what it looks like is your first eigenvector as a row, and then your second eigenvector as a row. This is now going to take your first eigenvector, for instance, if I write it as 1, 0, or 1, 0, like this, and what it's going to give you is v1 as a vector. So you have your vector v1. That's your result. It does the same sort of thing for v2. So this takes components expressed in your eigenvector basis and expresses them as the eigenvectors themselves. This is exactly what we want our change of basis matrix to look like. So if I make this matrix, this is my matrix S. A matrix constructed with rows given by the eigenvectors of your original matrix A. So we can take a matrix A in any basis, provided it has the right properties, find the eigenvalues, find the associated eigenvectors, and construct the matrix S, which, when multiplied by A in this format, will go from your eigenvector basis to the basis of A, allow A to act, and then convert back to the eigenvector basis. And we know that that has to have this diagonal form. So A prime is equal to S inverse A S, where S is given here, and it has this form, lambda 1, lambda 2, dot, 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 up to lambda n, with zeros off diagonal. So we have our eigenvalues along the diagonal, and we have zeros off diagonal. This is the process of diagonalization, and it will end up being a major component of quantum mechanics, since the process of finding the eigenvalues and the eigenvectors is associated, and we'll talk more about this later, is associated with the process of finding the stationary states of the Hamiltonian, for instance, if the transformation we're considering is a Hamiltonian. We'll of course talk more about that in detail, but for now, the last topic is Hermitian transformations. Hermitian transformations have a lot of nice properties which can only really be expressed in terms of the eigenvalues and the eigenvectors, which is why I put off their discussion until after we had discussed eigenvectors and eigenvalues. But to recall, a Hermitian transformation, we described it in terms of matrices. A Hermitian matrix is a matrix such that the Hermitian conjugate of the matrix, which is equal to the complex conjugate, transpose and complex conjugate of the matrix, is equal to the original matrix. There's another way of defining this, and in terms of transformations, the best way to think about this is as an inner product. Suppose I have some vector alpha, and I'm going to take the inner product of that vector with the product of what I get when I apply some transformation A to a vector beta. If a transformation is Hermitian, we have that this is equal to A hat acting on alpha, inner product with beta. Sorry, this is not just A hat, this is the Hermitian conjugate of A hat. So if we allow our transformation to act on the vector on the right of the inner product, versus we take the Hermitian conjugate of the vector A, or the transformation A hat, and allow it to act on the vector on the left of the inner product. This is the essence of taking the Hermitian conjugate of a vector. If we take this transformation and allow it to act on the right, we could equivalently take the Hermitian conjugate and allow the transformation to act on the left. So in terms of matrices, you can think about this sort of inner product, which is really poor notation because this A hat beta ket is not necessarily meaningful. You have to think about A hat, the transformation acting on the vector beta. But what this actually ends up looking like in terms of matrices, if we express something in a basis, we have the bra alpha, which let's just write that as A dagger. And then we have some matrix, and I'll use capital A, representing our transformation, A hat. And then that's going to act on the vector B, which is taking the place of beta here. I can equally well express this as the Hermitian conjugate of the matrix, which I keep writing as T, the matrix A, acting on the vector A, and that acting on B. So that's essentially equivalent to this notation. Taking the Hermitian conjugate of a matrix and letting it act on the left is essentially taking the Hermitian conjugate in this context. So what this actually looks like, the Hermitian conjugate now of a vector is, well, it's a complex conjugate transpose. So instead of having a column vector here, we have a row vector. Our matrix A is a matrix, as always, and B, not being Hermitian conjugated, is a column vector. When I take the Hermitian conjugate here, you can think about this as being your matrix, which is now Hermitian conjugated, acting on the vector A now, and then when we're done with that, we allow it to act on B. So I can take this sort of matrix vector product, and I can take this sort of matrix vector product, and everything is okay. So an operator is considered to be Hermitian if A dagger, in the matrix context, is equal to A, or equivalently if it doesn't matter if I allow this transformation to act to the right or to the left. It's a very useful property to have, and Hermitian properties have some, or Hermitian transformations have some really nice properties. If we have a Hermitian matrix, or a Hermitian transformation, or a Hermitian operator, depending on whatever terminology you choose, the eigenvalues of this matrix are real. And you can see that by looking at the expression, say I have some vector alpha, and I will then use Hermitian operator T acting on alpha as well. This, you know what T does to alpha. If we have the state, if alpha is an eigenstate, we have this sort of expression. So I know what T does to alpha. It gives me lambda times alpha. But if this is Hermitian, I can of course pull the lambda out and get the inner product of alpha with itself. If T is Hermitian, I can also allow this to act from the left, like so. These would then be equal to each other. And, well, again, you know what T does to alpha. It gives you lambda times alpha. But now we have lambda left multiplying something. And on the left here, we're dealing with a Hermitian conjugate of our vector. So essentially we have to complex conjugate lambda. So we'll end up with lambda star, and then alpha inner product with alpha. So if these two are going to be equal to each other, lambda equals lambda star, we know the eigenvalues of this transformation are real. The next key fact about Hermitian transformations is that the eigenvectors from distinct eigenvalues are orthogonal. And you can see that by much the same sort of reasoning we applied up here. Consider some eigenvector alpha, inner product with some Hermitian transformation acting on some other eigenvector beta. If I allow T to act on beta, I will get the eigenvalue associated with the eigenvector beta, alpha, and I'll call that mu. So this is going to get me mu times alpha inner product with beta. If T is Hermitian, I can just as easily as before allow T to act on alpha, T hat alpha from the left. And when I allow T to act on alpha, I end up with the eigenvalue associated with alpha, which I'll call lambda. So we'll end up with lambda alpha inner product with beta. As before, I can pull out the lambda here, but since I'm now on the left with the bra instead of the ket, with the Hermitian conjugate instead of the vector itself, I end up with the complex conjugate of lambda times alpha inner product with beta. If these two things are going to be equal to each other, and mu not equals to lambda, or mu not equal to lambda star, this can only be true, this can only happen if alpha inner product with beta is equal to 0. This is really nice because this tells you that the eigenvectors are orthogonal. And if you're thinking ahead, you think orthogonality is a really good property for basis vectors to have. And if you have an orthogonal basis of eigenvectors, then your transformation has a really nice form as well. The final property is that the eigenvectors span the space. And this is sort of true, but there's some caveats. Unfortunately, or fortunately, sorry, the caveats are not really all that important for quantum mechanics. If you have a transformation with n eigenvalues, and they are n distinct eigenvalues, you're guaranteed that the n distinct eigenvectors will span the space. Since if I have a space of dimension n, my matrix that is expressed in some basis, the matrix representation of my transformation will have n eigenvalues, and I will get n distinct orthogonal vectors. And the only way you can have n orthogonal vectors in an n-dimensional space is if they span the space. So those are some of the nice properties of Hermitian operators. This was a lightning-quick review, hopefully, of linear algebra. We will work with some of these concepts in more detail later. But for now, to check your understanding, here is another matrix, different from the one that I worked with. It's also 2 by 2, so these calculations are not terribly difficult. Your task is to find an eigenvalue and its associated eigenvector. Since this is a 2 by 2 matrix, and if you look, this matrix is also Hermitian, you know it's going to have 2 real eigenvalues, and the eigenvectors should be orthogonal, and you can go ahead and check those properties as well. But for now, just find an eigenvalue and its associated eigenvector. We'll be doing this sort of thing in the context of quantum mechanics, even with systems as simple as two-state systems where you have 2 by 2 matrices later.
Thanks for watching. Please subscribe and don't miss out on new videos and lectures.